Don't worry about the introduction, my friend.
That's so important.
No, because literally, I'm not going to even introduce you. I'm just going to be like, here it is. Hey, Benji,
Yeah.
I heard you have something cool to talk to me about. It's about time you got down here. By the way, you're highly sensitive to 5,700 hertz.
57.6. Don't forget.
So, you got something cool to share with me today.
Wow. Directly into it. Yeah.
Yes, let's do it.
So one of the things that I found like really interesting going through grad school is that Google noticed that, hey, you're paying attention to research that's like just coming out. You're looking at all these articles that show up on Google Scholarly. And so, you know how they have those feeds that pop up. One of the cool things that popped up is this paper right here.
So you got recommended this paper?
I did by Google. I didn't have to look at this. The algorithm's like, here's a nutty thing for you to check out, which is a paper from 2018 titled Quantum Theory Cannot Consistently Describe the Use of Itself.
Oh, this is going to be a Russian dolls all the way down.
Oh, yeah. So this is a paper from Daniela Frauchiger and Renato Renner. I hope I got your names correctly. Sorry about that. Now, what this kind of keys into for me is the idea of physics, how physics and science has consistently come in and destroyed our notions of how, like, our previous notions of how reality works. Even the previous scientific ideas that we have, further research says, maybe they're not right. Maybe there's something better. Or maybe there's something that just fundamentally breaks what we thought we knew.
Right.
And this is one of the most forefront examples of that. So I guess what I'd like to do is just shift and talk about stuff without showing my notes.
Go for it, man.
Okay.
So it's going to be screen mirroring. Yep. And there you go.
Got to remember how to do this bit.
And then once you click out of it, concepts will take control.
Yeah. So when we think about... Are we not working? There we go. When you think about the first scientific ideas that kind of show up, what's one of the examples that like pops into your head? Anything come off the top?
Well, first scientific ideas. Actually, let's go back to Greece. They thought everything was earth, air, fire, and water.
Right.
And then ironically stumbled upon the word that we now use for what matter is, but we didn't realize it was actually composed of atoms until, nearly 2,000 years later?
Yeah. when we looked at things and said, oh, hey, maybe they are indivisible.
Right.
Yeah. So that's one of the fun things is that originally the way that human beings thought about understanding the world was that theories that were good enough to describe how I felt the world worked was good enough as a theory. The idea of going out and testing those theories didn't exist back then, right? So one of the things that you brought up, Earth, Wind, and Fire, right? The four elements, that was an extension of an initial theory, an initial philosophy that the world actually was just made up of different types of water, which was then supplanted by Plato arguing, no, that doesn't make any sense. Look at these kind of examples that I think of. No, it's all about these forms that reflect a more perfect reality that then is brought down that we as imperfect beings in the world can perceive actual reality is. But again, it was all about philosophers kind of arguing with each other about how their word soup put together made more sense than the previous guy's word soup.
Right. It was all, I can argue this better than you can. Therefore, my truth is better than yours.
Right. It was all left to the realm of description, and no one actually sat down and said, hey, wait a minute. Let me see if that actually matches the theory. And one of the first times that we actually see this that I think most people are familiar with is with Galileo's work, right? There's a fundamental concept that we have when I mess with an actual physical object that how much something weighs, how much of it is there, really affects how it moves. And one of the how it moves in free motion. And one of the first things, well, one of the many things that Galileo showed is that our conception of that, if I like, for example, if I drop a bowling ball and a feather off a tower, I kind of expect the heavier thing to be less encumbered by the fluid of the air and to fall away. But back then, there wasn't really a concept of the air getting in the way. It was like, no, okay, I have a bowling ball, it's heavy. I have a feather, it's light. And when I drop them, I see that the bowling ball makes it all the way through, and the bowling ball hits the ground first, and the feather doesn't. And what Galileo says, hey, you're not paying attention to a constraint. You're not paying attention to something that gets in the way. Air. If I get rid of air, then the difference of how a bowling ball falls and how a feather falls disappears. And they land at exactly the same time,
right,
as long as I drop them from the same height. The idea that weight mattered for falling objects intrinsically was wrong. The weight only matters when you add extra medium for them to fall through.
Right.
Right? Another classic thing that he broke was the heliocentric model, the Earth-centric model. And
or what about epicycles?
Yeah, right. Jumping back to Greece, where Grecians were like, "Hey, man, this thing doesn't follow what a perfect circle would. Well, what if it's a circle on a circle? We'll just kind of add more circles until it's right."
Curve fitting 2,000 years ago.
Oh man, we can make the elephant dance with enough parameters. Now, once Galileo kind of popped in and started actually testing these things, a lot of the scientific method continued to we didn't have too many large scale disruptions in how we thought about reality for a long time. Even when Newton came along and described how gravity works, and that the thing that keeps the stars moving and us in orbit is the same fundamental thing that causes an apple to fall to the ground, right? That didn't really change how our understanding of being people and creatures in reality changed, right? I still expected my experience and your experience, regardless of whatever frame or how we were moving or other various factors changing, to be the same.
So do you mean you and I perceive each other sitting here, we don't question whether there may be something more going on than just what we're seeing with our eyes?
Right.
Because there was no science that led us to think that perhaps even our perception that we're having right now could possibly be flawed or incomplete.
Right. So I don't expect someone traveling on a train to really see things that are that different than me sitting down watching. If I watch an apple fall down and he's on a train traveling watching the apple fall down, I don't expect things like how far the apple moved to be different if we take into account that he's moving, right? But that actually changed with a couple of theories in the early 1900s, right? One of the very first ones, Einstein brought up his theories of relativity, in particular special relativity. Came along and said, that the fact that you're moving along on a train actually does affect the things that you'll measure. Some of the things that we took for granted, because in the previous mindset, I didn't expect the time that it took for an apple to fall on the ground to be different between someone who's sitting in a train and someone who's just sitting still with reference to that train.
Okay.
Right? But Einstein, because, and this actually goes back to the work that Galileo did actually in the math of how time changes, how you account for the changes in observation based on how something is moving relative to another reference frame.
Okay.
Right? That we still called them, when you study special relativity, you call those transforms Galilean transformations, because he's the one that first kind of started thinking of them, and then Newton adopted them into his theory of physics and how to deal with observers in different reference frames.
Okay.
Einstein says, wait a minute, it turns out that the notions that we have of moving through media, and this was inspired by noting in the previous theory on electromagnetism that electromagnetic waves, electromagnetic fields can cause each other to propagate amongst themselves, and that actually fits the form of a wave equation.
Well, you just got heavy here.
Oh, I really
You
did.
just threw a lot.
Yeah, that's too much.
Do you want to unpack that a little bit?
So if we're looking at a wave traveling through, let's say, water, right? I know that if I look at, wow,
At least it wasn't your 6K.
I was, who knows? I just noticed the sound. So like if I have, let me see if I can figure out how to work this. This is snap, right?
Was that supposed to be a straight line?
That was supposed to be relatively a straight line, yes.
I'm getting more of a wave feel from that.
Well, we're gonna get there. So if I have,
Wow, I just saw a blue circle.
oh, interesting. That's not at all what we're aiming for.
It's all right.
Concepts is what we want, but where on this, real quick, where on this is your back?
Okay. Which thing do you want to do? Oh, just
Well, one
the
I want to
undo.
undo, and then I want to
the
be
undo
able to.
arrow is right here.
Okay.
And if you ever get confused and you see, hey, there's a cut thing there, then that's because the pen got double tapped.
Okay.
So I just have double tap to go back between erase and draw.
Okay.
There you go.
And then if I wanted the snap function.
The snap function is going to be
It's here, and then hit option.
I wouldn't necessarily hit options if you just select it.
Mm-hmm. And then, oh, okay.
Yeah, or if you hold down on it, it should pop up a little context menu.
Yeah, that's the same as hitting options. Okay, so let's go ahead. Let's get
You
these.
missed then.
Yeah. So if I have, let's say, I've got the surface of the water, right?
Okay.
I'm looking at the ocean. Here's the shore. Here's the land. If I have, let's be real ideal. If I have a wave that pulses like this, right? A wave coming into the shore in this direction. There's two things that I'll have to pay attention to, right? Because we're dealing with motion and trying to track position. That means I'm paying attention to motion and time. So the position of this guy, of this wave front, is going to depend on what position I'm looking at and at what time I'm looking at. Okay. Now, there's a relationship between how this pulse moves through time and space, and the way that we do that is mathematically with something called a derivative. Effectively, what is the change of the thing on top over what is the change of the thing on bottom?
Okay.
We'll not give the argument of limits and all of that. We'll leave that for calculus class. But basically, right, for a wave equation, I want to say, okay, how much position changes, right? Excuse me.
Somebody's going to be asking, why did you just square that?
Yep, we'll get there.
Okay.
So here, these are the variables that I care about, and I care about how high is the wave.
Okay.
Right? So we're going to look at how... Give me here, and then, double tap. That's going to be so annoying. So we'll get there. This is quintessentially how this equation works. And I think I've actually... Yeah, I reversed this.
Unfortunately, you have an infinite amount of space. So if you just realize that you've hit a wall, you can just kind of two-finger drag it around.
Yeah, there we go. That select tool.
It's good to see your handwriting hasn't improved at all.
It's fucking terrible.
Oh, you figured out selection.
I did figure out selection. This
This is going to be a gangbusters presentation.
The bee's knees.
Yes.
All right. So, right, we were looking at this. If I look at that equation there, terribly drawn. My goodness. I see what you mean about trying to get through this content in under so much hours.
Oh, yeah, man.
So many hundreds of years.
You've probably got 20 hours of content.
Jesus.
Already lined up.
Can I? Come on.
And depending on what mood I'm in, I may just cut out some of just the times as you're figuring it out.
Oh, yeah. I would hope so. This is bad.
I might not, though. I might just be like, hey, I might make a separate video of just you figuring this thing out, and that will be the first video.
It's like, here's this idiot trying to be professional and understand stuff. So in this drawing, my brushes.
It's about the content, not about the tools.
Yeah, no kidding. Why? I wanted to make this whatever. I wanted to make it pretty, but
well,
why is this? Oh, that's why. So how do
and you see the color palette to it if you want to
there we
switch
go.
Colors around.
No. I was still stuck in selection, so now I can get back to it.
Okay.
How annoying. Right. So we can look at this and we look at the left-hand side of that equation and we go, oh, okay, this is...
Well, tell me first, what is this equation actually saying?
So it's telling...
Somebody who's not versed and doesn't know what a second derivative is. What are we actually looking at?
So let's look...
Partial derivative, not to mention.
Let's look at the classic way to do this. If I'm looking at what my position is, right, as a function of time, okay, that's just base. If I then ask how much am I changing as a function of time per unit of time,
okay,
that's velocity. That's your first derivative.
Understood.
Right now, so if we're analyzing this to the car, let's say you've got a car in a parking lot. Your position would be which spot in the parking lot is it, right? Which, if I numbered each of the parking spots that I'm driving past, are you by parking spot number 1, parking spot number 2, 3, etc.
Okay.
The first derivative would be what your speedometer reads, effectively.
Okay.
Right? And then the second derivative, which is how fast is that speedometer changing per unit time?
Your acceleration.
That's your acceleration.
Okay.
And that would map to what you feel as you press the accelerator.
Okay.
Right? Or the brake pedal. That's also an acceleration. Right? So here, since we're looking at a couple of variables. We're looking two-dimensionally at a height and a position along the water.
Okay.
Right? The math is going to get a little more complicated, but not much. So what I can ask for is what's the acceleration, the second derivative of the height at a particular point with respect to time?
Okay.
And what is the derivative, the acceleration of height with respect to scanning the position at a moment in time?
So you're saying I observe the wave to be, let's say, 5 dots over to the left.
Mm-hmm.
I want to know what that implies, how much the wave height is going to be changing per second.
Right.
Okay. Based on that current position of the wave. Okay.
And the thing that relates them is this factor of 1 over the velocity of the wave itself.
Okay.
So if I put that into Maxwell's equations, the theory of electromagnetism, what you find is that this pops out, and you actually have the constant that pops out here is the speed of light squared.
So you're saying out of this equation I'm looking at right now,
yes,
if I drop it into Maxwell's equations,
actually, you should have a squared there. Excuse me.
Out will drop
the speed of light in a vacuum. Yes.
Okay.
And what is interesting is that no matter how I try to then manipulate how a light wave will look as I'm moving through the so-called... So the analogy that I gave you here, right? The water wave required water for the wave to move through, right?
Okay.
So typically what is assumed about waves is that there is a medium that they are allowed to move through. If there's
stuff.
some stuff
Okay.
to move without actually moving the stuff. So the energy is transferred without transferring the matter with it, right? So
just to elaborate, so when you're saying the energy is transferred, in the case of the water, we understand that to be literally the water molecules just kind of banging up against each other. Okay.
Right. Think about like if I have a pond and I drop a really big stone into it, right? It's going to make waves, and those waves are going to go across the lake all the way to the other side of the lake, right?
My producer's telling me I'm saying okay a lot.
Yeah, that's a thing that people do in order to
It's all right.
confirm things. It's fine. So the water that reaches the opposite shore, right? When the wave reaches the opposite shore, the water in the wave at that moment is not the same water. It's not the same water molecules that were part of the wave way back when I first dropped the stone into the water, right?
Right.
So waves transfer energy without transferring the matter that started it, right? And it's done through the medium. For water waves, it's water. For sound waves, which obviously that's how we're talking, that is another medium, right? We wouldn't have any sound if you don't have the air around you, right? The classic tagline for those space horror movies: no one can hear you in space.
Right.
No one can hear you scream in space because there's no air, there's no medium. So back in the 1900s, people were looking for the medium of light, right? We didn't have a way of directly looking at it, right? Because light just kind of moves past a little bit too fast to really probe it. But we were trying to figure out how can we detect this medium, which was called the aether at the time. Now, one of the interesting things, right, if I think about waves in the ocean, how fast I measure that wave moving in the ocean depends on how I'm moving through it, right? If I'm on a boat and I make sure to ride, or actually, let's say I'm a surfer, right? As I'm paddling through the waves out to shore to try and catch one, I see the waves coming at me, but in addition, since I'm moving forward through the medium, I actually see the waves coming at me faster than the waves are moving if I looked at them from like a helicopter, for example, just sitting up top.
Okay.
Right? But the moment you get far enough out, turn around and catch the wave, all of a sudden you're moving at exactly the same speed as the wave, right? Because it's carrying you. That wavefront looks like it's not moving at all. And in fact, it's the earth moving underneath you. Now, what's interesting is eventually through experimentation, we found that that's not true for light. That no matter if I see something emitting light and I check and look at how fast is the light being emitted from that source, no matter what direction I come at that source from, no matter what speed I come at that source from, what I see is that the speed of the wave, the speed of the photon coming out of there, doesn't change.
Okay. So maybe let's elaborate a little bit on that. You gave the analogy of the wave and then the boat, and then you ride up and basically match the speed of the wave, and you're basically on top of it, and now the wave is not really moving anymore.
Right.
So why can't I just do that with a photon? Why can't I just lasso a photon and just ride that photon and go as fast as a photon? And why won't it just look like the photon is stopped?
Well, for one, practically speaking, it's very hard to move at the speed of light in a vacuum.
Okay.
Right. That is so far something that we haven't managed to be able to do. But that doesn't mean that we don't have experiments to actually check, right? There's Michelson interferometry. So using the fact that since we know light travels like a wave, right? Waves have peaks and valleys. And if I'm able to overlay different waves. If I have one wave that looks like this and I have another wave where, it doesn't help if I draw exactly the same picture now, does it? If I have another wave where its heights will look like this, right? It'll have a low point where this guy has a high point. Mm-hmm. Assuming I've drawn this well enough so that their peaks match, which, clearly I haven't, but that's fine. Right?
It's implied.
Right? What's fun... Wow. Let's see if we can... Oh, we did it. Right. If I bring this over, a principle called superposition. So what I'll actually measure is the addition of these two things. Right. So I won't measure just the peak of this and the peak of this separately. If I look at the height in this, what I'll see is the addition. And if they're oriented, right, if I have two waves superimposed on each other and they're completely out of phase, but with the same amplitude, the same height in the wave, what'll happen is they will, instead of having some wave, they'll end up canceling each other out.
Okay, so for those people who maybe aren't fully versed on special relativity and the implications that light is always moving at the same speed, what you're saying here is in response to my, why don't we just lasso the photon and ride it and then it looks like it's not moving anymore? You're saying, well, the only way we could have done that is by using another photon to keep going at the same speed as it. And then when if that photon didn't line up, if its waveform didn't line up the same way, it would actually end up canceling out the other one.
Right.
As opposed to being like, oh, you're going no speed at all.
So what you can do is, effectively, since we can't move at the speed of light, we have to use this superposition and the fact that waves, what's called, interfere with each other.
Mm-hmm.
They either make, one wave on top of the other can make it bigger or it can make it smaller.
Okay.
Right. And we can use the fact that we can have two different photon sources, let's see. Yeah, we can use the fact that you can have one source interfere with itself by splitting, doing partially backed mirrorings.
Now you realize you just dropped a little truth bomb here. Because now you're saying a single photon can interfere with itself.
So let's just say that we have two photons that we know. Through tricks, you can use it through one photon, but it doesn't matter. If you have two photons and you know how they are, how they're in phase or out of phase with each other, what you know is that if your photon is going to be, if you are like in other wave theories where I am sensitive to the direction that I'm moving at with respect to the medium of the wave, and I'll measure different velocities for that. What you can do is use the fact that the Earth is moving, and the Earth is moving through, this supposed ether. If I can rotate where the sources are emitted from, then what happens is I should see the one that is in line with the motion of the Earth's motion through the ether.
Okay.
Right? If I put them at perpendicular, there will be one that's aligned with how the Earth is moving, and then one perpendicular with how the Earth is moving through space.
Okay, so we're back to the scenario now where you originally described it, the waves, we have the water molecules, and that's how we measure with water. Now we're trying to find the substance that light is traveling through. So now what we're trying to find is evidence of the substance that light is traveling through. Okay.
So we're going to need to have you make sure that this stays on for long enough.
Pretty sure I did.
Well, it just turned off, and I didn't press the power button. Anyways, so to continue this conversation, to continue that point, what we're trying to do is we're trying to look for, these experimenters are trying to look for the evidence that there is some medium, and the way that you look for that is by looking for, does the difference in the way that you are moving through the medium affect the speed you see those waves in the medium move?
Okay.
Like, how fast are they moving?
I see.
Right? So if you have them, right, let's say we've got Earth and it's moving through the ether like this, right? I can have my experiment set up so that there's a photon source here and a photon source here, and then I'm detecting their interference in this direction, right? If I have a mirror, a half mirror, that'll let some of the light through, and this will bounce some of the light. Some of the light will be bounced backwards, but I'm not measuring that, so it don't matter. Now, what I can do is you can set this up, right? If it's just a flashlight that I know the phase that it comes out at, and let's for sake say I can do that. 2 flashlights, I can put this on a pinwheel and rotate this whole thing, right? So that now I'm detecting here, I'm detecting perpendicular to the motion of the Earth. I've got one source here directly in line with where I'm detecting, and one source perpendicular. And so if this is source 1 and this is source 2, I've rotated them like this. So I've gone from having the photon from source 1 being in line with the motion of the Earth through the ether. And in theory, at some point, I've shifted it so that...
Can you draw like the orientation of the beams that are coming out of 1 and 2?
Yeah.
Oh, no, not the one on the left.
Here. Well, was I drawing the orientation? I suppose I was. Yeah. So we have it coming out here. Like that.
Okay.
Right.
I see.
And they're combining
I see.
into this bit there.
I didn't recognize the
Sorry.
lamp.
Yeah.
Don't worry.
These are lamps, and this is your detector here.
Gotcha.
Now, in theory, if as you're moving through the ether, the orientation of the source of light relative to your reference, your reference frame as you're moving through that medium, right? I should see a shift between, let's say I've got light in my detector, right? As I rotate it, I should shift how much interference or constructive or constructive interference there is between those two sources.
And those, to be clear, that's the interference that you described over there.
Right.
Okay.
So as I go from one setup to the rotated other setup, I should see a change in the intensity of light that I'm detecting.
Okay.
Right? If you do it real good and have it set up, you in theory should be able to go from having light there to, as you're rotating, no light. And then as you further rotate it, light again. Right? Now, for those versed in this will know that, in fact, the experiments did not see that result at all. The intensity of the light at the detector stayed the same the entire time.
One of the most spectacular null results ever.
Yeah. So what people had to do was go, well, geez, how do I account for this? And effectively, what happened is that instead of what turned out to be the incorrect assumption is that the idea that the amount of time that's perceived for someone who's moving versus someone who's moving in a different direction or a different speed, or someone who's just sitting down, that the time that they see an event taking place, if they're all watching, say, an apple fall down from a tree, that actually depends. It's not the same time. Let's actually say...
So hold on, let me stop you for a second. Just so the implication is clear here. You're saying that the reason why this is we've determined that there's no ether, and therefore the speed of light is always constant.
Yes.
And because it's constant, because an event is here and an event is here, because the light takes longer, or here and here, the light takes longer for here, I'm going to perceive the event here occurring at a different time from this event.
Right. So if you have, let's say you have two people playing catch, right? And you measure how long it takes to go from dad to son, right? A person sitting down will measure a certain time. If there's another person traveling in the direction of the ball, but let's say they're traveling really fast, right? Someone on the train, it'll look more or less the same. But if you're traveling really fast, it will actually appear that it takes a shorter amount of time for the ball to go from the father to the son. So what happens, and this is the weird thing, is that in order to make sure that you measure a constant speed of light, space actually distorts. It shrinks or extends depending on how you're moving.
It's a pretty profound statement,
isn't it? So our perceptions and what we actually measure differ depending on what reference frame we're moving in, even if they are both inertial reference frames.
So define inertial reference frame.
So an inertial reference frame is one that's not experiencing acceleration, or it can be basically approximated to not being experiencing acceleration, right?
Okay.
So you and I sitting down have a relative reference frame.
We're both anchored to this table.
Right. Now, the moment I try to account for something far away, I have to, account for the fact that the Earth is spinning, and that's technically an acceleration. But as far as local things, we can approximate it as being acceleration free. But the physics that you and I see are going to be different than the physics someone else jumping up and down, for example, we'll see, right? Because they're experiencing acceleration briefly and not enough to really, do anything useful or see anything trippy, but it's there. So the fact that time and space contract and lengthen in order to maintain the constancy of time has an interesting consequence. In particular, the notion of simultaneous things, simultaneity, is gone, right? So you might look at me and go, what the heck is simultaneity? Well, actually, it's a perfect example is let's go back to Galileo doing his experiments with the bowling ball and the feather. Let's say he's on the Tower of Pisa and he's managed to remove all the air around himself without suffocating, and he's doing the experiments dropping the ball and the feather. Now, he stands and makes sure that they're exactly the same height and drops them at the same time, watches them land at exactly the same time. And he goes, aha, my conclusive result is that weight doesn't affect how objects fall without air resistance to mess things up because I see them land at the same time. But if someone is traveling across is traveling perpendicular to the objects falling at a very high speed, it actually isn't true that they hit the ground at the same time according to that observer. Okay. What'll happen is, depending on the direction that they're coming in and out from, the direction that the other observer is moving will tell them whether the feather falls or whether the bowling ball hits the ground first. Now, granted, that doesn't really invalidate his Galileo's reasoning that the weight doesn't matter, but you will still have a difference in what hits. And if someone is naive, although someone traveling real close to the speed of light, presumably they understand enough science not to be naive, but someone who's naive seeing that would say, oh no, clearly the bowling ball, if I travel this way, I see the bowling ball hit first. The weight matters. Or someone going the opposite way will say, no, the feather matters. So in fact, lighter objects fall faster. Right?
Interesting.
So fortunately, we reached these results in kind of sequential order. So we kind of knew that weight didn't affect things before we did relativity and said, oh no, how do we even reconcile what this is? But yeah, the notion that things can happen simultaneously and be agreed upon by all inertial observers is actually not true. And that's something that we thought was true for a vast amount of time in the history of physics, right? Newton thought that if he watched Galileo drop his objects from a train, he would agree with Galileo's observed events that they both hit the ground at the same time. But it turns out Einstein comes along and says, no, if I speed this train up, you will not agree with Galileo.
Now, is there any way to reconcile that?
So, effectively, no. If I have two events that are what are called space-like separated, that is, well, let me put it in here. If I have two events, let's call them, let's say I've got position here, time here. I've got event A here and event B here, right? So this would be what it would look like for someone who is standing still, right? What these events.
Puppy into the middle of there you go.
Yeah, that's probably a good idea. So these events, right, according to this observer, occur at the same time but at different distances, is what this tells me, right? Another reference frame, what it'll look like if I'm moving at some amount c, will be position here, and
So the implication here
time there. And what this
is we now have acceleration. The people with the blue lines are experiencing an acceleration.
not acceleration, a different velocity.
A different velocity.
Mm-hmm.
Okay.
And notice, so if I'm measuring, so all the events along this line, these are what will be assigned the same time in this observer's reference frame. And notice A and B no longer lie on the same line. What'll happen is that, oh no, I assign B an earlier time than I do A. And there's no way to, through the math of relativity, come to a conclusion of which event happens first. It all is observer dependent. It's all reference frame dependent.
Okay, so I'm sure you realize the next question is going to be, what if both people have a clock and they synchronize it ahead of time? And then both observers observe it, and then they write down on their clock, and they come back later, and they compare results. Can you reconcile the situation at that point?
So that comes back to how time transforms in order to maintain the speed of light. So if you take the measurements that you take in one reference frame, put them through the transforms that we have that take you from one moving reference frame to another reference frame moving at a different speed, then they'll agree. But the time that each person says locally it takes for one event to happen than another will not agree in their reference frame. I can always transform my results into the other person's reference frame, and I'll get back what they say. But what that means is that there is no conclusive way of saying that they both happen at the same time.
So I have a stopwatch.
Mm-hmm.
You have a stopwatch. We're both moving different speeds, different velocities. We both observe the event, and then we stop it. Let's say our timing's perfect. And then we come back, and we compare that time. We show each other. Those numbers are not going to be the same number.
No. Yeah. The interval between when those two events happen actually changes depending on your speed, right? That's the Lorentzian time transform, right? It's some good stuff.
First few weeks of modern.
Yeah. Because it turns out Lorentz and Poincaré kind of working through trying to figure out how this Aether stuff worked. Back before Einstein was like, oh no, we should pay attention to the constancy of time. They actually discovered this whole transform for local time and then just kind of disregarded it, not giving any physical reasoning for why it would pop up. There's just this is convenient. So here we go. And so they left Einstein to make one of the biggest discoveries of human history instead of themselves. Whoops.
I wonder how many times that happens.
Well, I mean, you can just look at Newton and Leibniz fighting over who came up with calculus first, right? So yeah, our notion of how time and space interact is flawed, and what that tells you is that the everyday expectation that I have, the perception that I should agree with someone moving on a train, because why would they measure time and space differently, right? They're just moving a little bit. Right? That notion's wrong. Science came along and said, yeah, you had this idea about how things work. No, it's actually incorrect. If you follow the evidence, test the world around you, the only conclusive way to get correct predictions leads to you realizing that the world has to operate differently than you intuit. Differently even than was better intuited by someone first producing science than someone just thinking about how it worked back in the Grecian times, right? And this kind of shows us is that science as a tool, it's very interesting because what it does is it just gives us better approximations of what's actually going on. And
seems to me like it's doing the reverse. It's making it harder and harder for us to agree.
I mean, yeah. it Oh goodness, yeah, that's one way to interpret that. What you have to do is you have to say, okay, how do we account for the things that actually do separate us? But it allows us, because we would have if we didn't know this theory, we would have disagreements with, how long it took things to happen. Imagine if we ended up being a spacefaring civilization with the technology to travel between stars in human lifetimes, but somehow we didn't discover special relativity. And then all of a sudden the lawyers try and come in and say, wait a minute, this and this happened. And then the other planet's lawyers say, no, it's exactly the opposite order. Can you imagine the kerfuffling that would happen? It does not take much thought to be like, maybe that should be a topic on a Star Trek episode, because that would be funny. That being said, right, the knowing that theory, it's then very important to know that this is how events can be distinguished, right? But that simultaneity isn't isn't a universal thing that is protected by how physics works. No, the simultaneity of two events can be shifted around based on how you're looking at things. And it's important to know that that's happening so that you can figure out by either inversing, transform, whatever, so that you can come to a place where two different observers who see irreconcilable things can say, oh, what's going on is that these are things that are space-like separated, and show any ordering that I give, any time ordering I give to them doesn't really matter for what's happening physically, right? So the idea is that if two things events A and B are space-like separated, so their simultaneity, their ordering in time is arbitrary, fortunately, they also can't influence each other. A can't be the cause of B, and B can't be the cause of A. So we're saved, in a certain sense, from that mattering to the theory, right? If you have,
so let me cut in for a second then. So what you're saying is that bowling ball's falling and the feather's falling.
Mm-hmm.
There's no way they could have affected each other's fall.
Exactly. There's no way that the bowling ball landing could have been the cause of the feather falling. Right? No reference frame, no amount of speed that you put into how you move through the universe will tell you that because the bowling ball hit the ground, it caused the feather to hit the ground at this moment. Right?
I see.
They have to be caused by something else than just those two events, right? If you want to get like in a more interesting example would be, let's say, two space cowboys dueling, and they happen to fire at the same exact moment according to someone who's referenced sitting still exactly the same between them, then there will be no way that you can have a lawyer flying at a speed so that he says, no, this guy fired in response to the other guy.
Okay.
Right. No matter how you look at it, even if you can say that, one fired before the other, what you can't say is that one guy firing, caused the other guy to fire.
This reminds me of that. Yeah, did Han actually shoot first?
Yeah, 100%. That's kind of what I was thinking. It turns out they're close enough, and there was enough time for light to travel between Han and Greedo, so that there is a actual order that things should be.
Okay.
You can't say, oh yeah, George Lucas just knew special relativity, and the new updated version was just moving through space at a different reference speed.
Right.
No, there is an objective fact that Han shot first. So simultaneity is gone, right? But it turns out we can kind of live without it, but it did change the way that we looked at physics, right? Now, one of the other big theories that came in and said, hey, reality and the world that we live in is definitely not what we intuit, is, well, the other big theory that was created in the early 1900s, that of quantum mechanics.
All right.
Yeah. that fuzzy little theory about how the smallest particles in the universe work, right? How does an electron behave? How can I figure out where its position is, predict how it's going to move through space? That's all quantum mechanics. And it came in and broke our intuitions, which is great. One of the most important things is that quantum mechanics, unlike every other theory that we've had of physics before it, is probabilistic, right? The notion is that the best that I can do in preparing an experiment is not to be able to, with my theory of quantum mechanics, predict exactly the result I'll get, but instead predict the probability that I'll get this result and predict the probability that I'll get the other possible results. I can narrow it down to a finite number of possible results from an experiment, and then the best I can do is what's the probability that I select any one of them when I actually measure the system. Yeah. So in a certain sense, quantum mechanics is it's a fuzzy picture of the world, right? And what's interesting is this bothered very much our big boy Einstein himself, because not only did he work on relativity and, produce one of the biggest theories, right, that we use today to understand how the universe works, but he was also instrumental in understanding how quantum mechanics works with his the electrophoto effect, and then as his own experiment that he did, and then actually coming in and saying, no, I hate how this theory works. How can I prove that it's wrong? How can I prove that this theory it doesn't know what it's doing? There's something just fundamentally broken with it, and we should abandon it post haste.
Okay.
Right? Because there's a couple of things that he didn't like. Specifically, he didn't like how fuzzy it was. He didn't like that it was only probabilistic. To make the famous quote, God doesn't play dice with the universe. He didn't like that the theory implied that the best you could do was have probabilities and not know exactly where things showed up.
So if you don't mind, let's go back to the feather and the bowling ball for a second.
Mm-hmm.
And I understand that you're going to want to put some caveats onto this because of the size of the object.
Sure.
But let's just go a little fundamental here. So what we're saying is quantum mechanics is not going to tell me for sure that feather is going to hit at the same time as a bowling ball, but it's going to give me the probability that it would fall and hit at the same time.
Yes. So effectively what I would be able to do is look at the bowling ball, right? So if I wanted to, let's say I could drop electrons, right? A bowling ball is an electron. A feather is a different type of electron. Let's say it's a muon, right? We've got muons and electrons. Bowling ball, feather. And let's say I'm dropping them and pretend for a moment that gravity actually affects those single particles. What quantum mechanics would be able to tell me is I would look at each one and poke, I would measure where is the position of the bowling ball, and then sometime later ask, where is the position of the bowling ball? And what I'd have to do is, if I were trying to string this together, basically keep measuring until I got the bowling ball to be like, yes, the bowling ball is up top, and now the bowling ball is at the bottom. And then I would have to do the same thing with the feather. What's interesting is that I would, in fact, have to measure that many times. I'm not guaranteed that, one, that I don't get, in this hypothetical, that I don't necessarily find the bowling ball in the middle first, and then all of a sudden, when I look away and look back, that it's at the top, and then look away and look back, and then all of a sudden it's at the bottom, right? In a very unexpected way, I not be able to determine exactly where the bowling ball is, right? Because one of the weird things about quantum mechanics is effectively you are stuck measuring one thing at a time. And that has some really, really strong implications on what you're able to do. So for example, right, because if I have a macroscopic thing, right, like a bowling ball, but actually let's jump to a different thing. If I give you if I give you a picture of a pitcher throwing a baseball, what are you going to be able to tell about the baseball? Well, pretty nicely, you can tell exactly where the baseball is relative to the pitcher that threw it. But if I ask you, how fast is that ball moving? What can you tell me about it?
While he's still holding it, or after he lets go of it?
After he lets go of it. You've got a picture of a baseball midair, a pitcher who has obviously thrown it, and it's traveling towards the batter. Or maybe just a catcher. Let's just simplify it.
So I guess the answer to your question is very little to nothing, because he could have faked the pose and somebody else could have thrown the baseball.
Very true. Right. There is it could be that picture, right? Just as you point out, could be explained by the pitcher throwing it at a certain speed and then taking it at a certain time. It could be thrown by another player in a different direction. It could be that someone on top dropped the ball down. You have no idea how fast that ball is moving, in what direction the ball is moving. When you take a measurement of its position, you are limited to knowing only where that ball is. And something like its position is just gone, right? Or excuse me, its momentum is just gone, right?
So the catcher is sus.
Yes. Because it can be explained by multiple different, position vectors, I can no longer say anything about the position. If we think about how we would measure the velocity of the ball as a single number, in fact, the way that you would do that is you would use a radar gun. But a radar gun will pick up velocities from multiple different positions. So if I measure its position, I lose the information if I measure its velocity, I lose information on its position.
So could you elaborate a little bit on that? Like, why is it that if I point my radar gun directly at that cup, let's say the cup is flying through the air from here, or I do it from over here, why would I get different velocity readings versus knowing where its position is? Like, why is one exclusive to the other? Like, what causes that?
Well, so it's basically a bit about how the instrument works. For the speed measurement, usually what you do is a radar detector, right? And so that's sending out just a wave that then bounces off the object and sends the information back to you, and then it uses the interference in order to calculate how fast whatever that radio wave bounced off of was moving. So because of that, because of the wavy nature of stuff, right? It's just sending out things in an arc, and it can only tell basically the expected height. Actually, I couldn't even tell the expected height of certain distance away, just the difference in that and how fast something moving would cause that to deflect. So basically, the height of...
So it's measuring multiple times to get that velocity reading.
In theory, for the radar gun, it doesn't necessarily have to measure multiple different times, but there are multiple. But what it does is it measures basically the difference in the peak that it sends out and the peak that it receives back at that moment. Like, because it's reading the peak that it sends out, and then what is the intensity or the peak that it receives at a certain moment of time. Says, oh, what's the difference in that? And there I can correlate that to a velocity of something moving across it. But because of, if I have a wave, it's sending out a sinusoidal thing, right? So that's just a lot of peaks and valleys. As time goes on, there's multiple peaks that all correspond to the same height. There's multiple positions that all correspond to the same height in the radio wave, the same intensity of the radio wave that's being sent out. So it can't tell you which of those peaks that the object move across to give you that speed. So there's a fuzziness in how far away from the radar gun it is, right? So when I'm making fundamental measurements, I'm reducing what I'm seeing and I'm trying to measure down to a single number, I have to exclude all of this other information. We're lucky as humans, right? If I watch a pitcher throw a ball, I can tell you its position and its momentum all at the same time. But that's because what my brain is able to do is take effectively multiple pictures and tell you, oh, okay, this picture was at this time, and then this moment later it was at this time, and this moment later it was at this time, and extrapolate the momentum information from all of those slices of all of those pictures that my brain took, right?
Okay.
Now, one of the weird things, so effectively to try and replicate that in quantum mechanics, right, would be, let's go back to the bowling ball falling down, the muon falling down from the tower. If I wanted to replicate that same kind of thing, that my brain, takes a picture at one moment, then a little bit later takes another picture, then another picture, then another picture, then another picture, and extrapolates, oh, okay, across this amount of time, I took this many pictures and saw the position change this much each time. What that would correlate to in our experiment, in our dropping experiment, would be, okay, here's what quantum mechanics, I've predicted this thing that's the probabilities that's called a wave function. Check what the position is at this time, then look away. Check the position at this time, look away. Check the position at this time, look away. And then hope that there's some sort of correlation, some sort of correlation that I can make between how I see the position move and the time in between the times I take those pictures. Now, what's interesting is that, getting this off screen. What's interesting, that cut out for a moment.
Yeah, that was weird.
Maybe I peaked or something. What's interesting is that the way that quantum mechanics work, and this leads to lots of consternation and philosophical implications, is that if I look at a wave function, if I probe it and say, okay, where are you? The theory tells me it gives one result. Out of the myriad of possible results that it could give you, you'll find and you'll get one of the results according, empirically, to the probability that the wave function predicts. If I don't give the system enough time, like if I keep looking at it and if I keep the measurement on that says, okay, where is your position? And I keep staring at that muon, at that bowling ball falling down, it stays there. It doesn't change. The result that I get from performing a measurement does not change as long as I'm actively performing that same single measurement.
Okay, so walk me through that again.
So if I think about it this way. If in the macroscopic world, I took a camera, right? That was the way that we measured position. I could hold open the shutter, and as the baseball is flying through the air, right? The measuring apparatus will get a bunch of different results, right? You'll get a smearing on the thing, and then granted, I lose, where the ball was, but I'll get all of the different possible results of measurement of position that the ball could have, right? It'll cause a smear of the ball from the pitcher's hand all the way to the catcher's hand. Quantum mechanics, if I look at a quantum mechanical object and I hold the camera open, I point my measuring device, my camera, at the thing and say, okay, where are you? Right? Take a screenshot. It'll give you back a result, but it'll hold that result. Your system will not evolve as long as you are taking that same measurement. Now, if I close the shutter and look away and then open the shutter again, I can potentially find a different result, so it'll have moved.
So we're talking some weeping angels type thing here.
Yeah, actually.
Doctor Who. So you look at them and they stop moving, and then as soon as you look away,
right,
and look back, they're closer.
Right. Now, what's interesting is if I don't give enough time between when I close the shutter and open it again, I'll get that same result. The wave function, as is kind of described in a Copenhagen interpretation. So there's kind of an idea, there's an idea of how, there are multiple ideas about how to explain the fact that we can get the different possible results from a quantum measurement. The most typically taken is this Copenhagen interpretation, which basically says that when I measure the particle, the wave function that describes it goes from being spread out across all possibilities, and the moment I measure it, collapses and chooses one of them according to the probability of selecting this one or that one, right? Chooses one of them and collapses so that the only thing that I can get is that result until I stop probing it, until I stop taking that measurement, until I close the camera shutter. And once you've closed the camera shutter, the wave function will then spread out from that collapse, spread out back to what it was before I ever took the measurement. But if I do that too quickly, the wave function doesn't have enough time. Now, granted, it's still pretty quick, so you have to take that, close and open it real quick.
Mm-hmm.
But it'll actually force the wave function to collapse back again onto that same result.
Interesting. And we have experimental evidence of this?
Yeah, you can look at particular I believe I don't know the authors that did this, but you can look at whether a uranium atom will radiate or not, and as long as you are looking for whether it is radiated or not, it won't. Right? It'll
Well, why didn't Japan know about that? That would have been convenient.
Well, because it turns out quantum mechanics, when you scale it up to the macroscopic world, that type of quantum mechanical freezing goes away, which, is kind of the reason why I can watch a baseball fly through the air and my brain can process it and the ball is allowed to move, right? So at some point, if you have enough stuff together, even if it's all quantum mechanical stuff, somehow it interacts in such a way that those quantum mechanical properties, these weird things about, these wave functions, collapse down onto what is observed on the macroscopic scale. And these measurements that freeze them, this is the only result you can get as long as you're taking that measurement, kind of goes away. Which, that's a weird thing. And it's actively one of the things that we're trying to figure out. We don't know why quantum mechanics behaves that way, and we don't know where the line between the systems that will have these quantum properties are, and where that line between systems that are quantum mechanical and have these weird properties of being frozen, where they can only be measured one thing at a time, and where we get to the macroscopic world, where I can set up a camera and set up a radar gun at the same time to measure the position and the speed of a ball at that moment in time at the same time.
So we're not sure how big something needs to be before this quantum phenomena does not become the dominant phenomena.
Right.
Okay.
We don't know where that line is, and that is actually that's an important thing. In fact, that's part of one of the arguments that paper was reading is trying to explain, right? Depending on how big you allow quantum mechanics to get, right? It stops being able to consistently describe itself. Yeah, you run into a thing called the Wigner's friend problem, which we'll get to. But it's another instance of our understanding of reality, physics, our study of physics coming in and saying, yeah, you actually don't understand how the world works. Your intuitions are broken. And quantum mechanics is one of the most straightforward way of saying, hey, you really don't understand how reality works on this level. We don't know what distinguishes on the microscopic level. And what's fun is we've had the theory of atoms for ages, right? Particles. We know that you and I are composed of these small particles. And what's strange is that we know those small particles all behave under this quantum weirdness. They have to follow these strange fuzzy rules that while we don't understand the why they're there, we can predict and have math for how it goes. But then we don't understand, why don't I see it on the macroscopic level anymore? We don't know. We don't know why you and I can perceive us being exactly here and not being spread out across a possible region of different spaces.
Or there's some interpretation of quantum mechanics where we are actually spread out
Oh, yeah, that's a thing. Um,
Can't trust atoms to make up everything. Nice.
So, obviously, so let's see. There are more big picture stuff that I go over before that. I think we're there. So, yeah, like I was saying, Einstein saw that and hated it.
I can see why.
Yeah, he was like, "No, I see reality, and I like, I'm all right with having constant velocity being the thing that shifts. I'm all right with time and space contracting in order to match stuff, but I should still be able to look at, some initial conditions and be able to predict from that, develop a theory that says, okay, as time evolves, the object that was here that I cared about is going to end up here, exactly there at exactly this momentum, right?
Sounds like determinism.
That's exactly what it is. Einstein believed that things should be fully determined, that that if you followed, something you were interested in, a ball rolling down a hill, or a rock just sitting there, that if I followed its history, at each moment in that history, I could have predicted how it got there if I knew a little bit more about its history, or I could predict where it would end up a few moments into the future and still be pretty correct. Quantum mechanics comes in and says, nah, you can't do that. The best you can do is have a probability of where it will end up, right? You can know exactly where a particle is at a particular moment in time, but because of, partially in part because of that inability to measure multiple things at once, I can't measure its position and its momentum at the same time, then I lose my ability to tell you where exactly it will end up. So the best I can do is give you a probability, a probability distribution over the range of where it could end up.
So it sounds like every time you describe another concept to me, you claim that we know more and more, but I'm hearing from you we know less and less.
So we're able to get better and better results for predictions, interestingly enough, more and more accurate predictions, but at the same time, we are giving up the philosophical intuitions about how we think things should work. So, right, like it goes back. We can jump back to Galileo as a perfect example. We give up knowing. We have a better ability to predict how things should happen by knowing that there are extra constraints that come in, extra factors that come in that we didn't realize were extra factors that we could get rid of. So, for the example of Galileo, I can talk about it was air resistance that causes the difference between heavy objects and light objects landing at different times. But then if you get rid of that, then the theory of gravity just doesn't care, right? And what that means is, yes, you have removed a thing that you thought you understood intuitively. That is, heavier objects will fall faster than light objects. But that would have led you to have incorrect predictions if you tried to apply it beyond that moment where your intuition was telling you the correct thing, where your intuition happened to tell you the correct thing.
So we're progressively discarding intuition in favor of greater and greater empiricism?
Yeah. I think that's a fair way to say it. We are in kind of an abstract sense. Let's say you've got a curve, like if you're doing an experiment and you measure stuff and you've got basically a curve that shows up. What you're doing is right, actually, let's just draw an example. This is your actual results, right? And my intuition tells me, well, intuition would predict that this happens. in this region here, it's a really good prediction. But if I go over here, it's really bad. So what we're effectively doing with science is coming up with theories that more accurately predict what are actual results. But we're never necessarily guaranteed to find the fully correct thing.
But we are getting closer and closer to mostly correct.
Yes.
Okay.
So the discrepancy, so like if I then say, okay, well, get rid of this intuition, and instead here's a theory that got rid of that intuition, but I can predict better, right? Now the region of where I'm able to predict is much longer, right? This bigger region matches, and then it's much later that there's a discrepancy between my results and what my theory would predict, right?
I see.
And how, we've gotten pretty darn close to some of these actual experimental results with what our theory can predict. It's a bit beyond the scope of this, but like quantum electrodynamics, right? The theory that marries special relativity together with quantum mechanics and a little bit of the strong force is the most accurate theory that humanity has ever produced. I think it's accurate up to 14 decimal places between what the theory would predict and the actual result if you measure that in an experiment. That is beyond the scope of this talk, but by embracing theories that seem strange on an intuitive level, we are able to make predictions that are closer to the things that we actually measure. So we might lose intuition, but we're gaining predictive power, right? So in a way, right, that's what we're talking about when we're saying we understand things better. Even if we are currently in a space where we don't quite understand why it's these theories that are the ones that best predict the results.
I see.
Right? It's not entirely clear quite yet why quantum mechanics is the theory of the small things. But the more we understand and are able to test away the intuitions that we have, the wrong intuitions that we have, the more we'll be able to limit why it has to be this way.
But are we slowly giving up our ability to explain why as we get deeper and deeper into this rabbit hole? Are we losing explanatory power, not as in the ability to explain the results that will happen, but why they happened? Because our intuition is telling us, well, the bowling ball falls faster because it's heavier. It's just, it's more mass and it'll want to go faster towards the earth. Well, that's our explanation, even though it's wrong. But we've lost that intuition and that explanatory reason. Now, granted, we're still in classical, so we haven't lost it all the way. But is that what's happening with quantum?
No, because what you're doing when you're replacing intuition with a more accurate theory is effectively taking one theory and replacing it with another, right? And what you're saying, but when you're doing that, what you have to remember, this is a fun bit, is you always kind of have to start with some assumptions, some baseline assumptions about how the world works. Now, initially, our assumption was what I see and can intuit must be how the world works. But then you go, no, what you're intuiting is the behavior across a small section of reality. And when you try and extrapolate beyond that small section of reality, the rules then it gives you inaccurate predictions. But the reason why what I observe on this level should be taken as the baseline truth is truly as arbitrary a reason to pick that assumption versus picking, no, it's just the postulates of quantum mechanics that rule the world. There's no real reason to pick one over the other if you don't have experimental evidence aside from one making you more comfortable. Effectively.
So the proof is in the pudding.
Yeah, it's basically this is where we dip into philosophy. We dip into well, just a bit of Descartes, right? The original experiment of I think therefore I am, inspired by, well, maybe what I see isn't right. Maybe my assumption that what I experience is real is incorrect, and in fact, I'm a brain in a vat that's being tortured by a demon.
Mm.
Right?
Hey, Billy, turn my headphone volume down just slightly.
And this reality is how the demon decides to torment me. Right? And the rules of this reality are no more consistent than the whims of a demon. And yeah, like that is one of the difficult, frustrating pieces, is that it's harder to pick your assumptions. But what science does is says, okay, we will assume that the things that we measure are what we should match. The things that are measured in experiment empirically are what are the ultimate arbiters of what is real, what theory ends up having the best assumptions.
I see.
That's the way you distinguish one set of assumptions over another. So even though it might make us more uncomfortable to think about reality being fuzzier than what I see, or, time being a stretchier concept than what I perceive at my low velocity self, that doesn't make it the better thing to choose as your baseline assumption.
Okay.
Right?
So follow the facts.
Follow the facts.
Wait.
Follow the things that we can all agree upon. Right? The idea is that if the fundamental idea of science being that I can make measurements on a system, do some experiments and get some results, and if someone else comes along, regardless of who they are, regardless of their history, if they follow exactly the same steps that I have done, they will get exactly the same results. And that agreeance between those two experimental results is what says this is what should be the basis of our reality, right? So,
speaking of reality,
Einstein hated the fact that quantum mechanics told us that things should be fuzzy. Could not stand it. So what he comes along and proposes is that, well, maybe reality, maybe nature herself is not fuzzy. She knows exactly where the particle is. What is the problem is humanity, and particularly how we measure things, right? Maybe as far as what we're able to measure so far, right? Because there's no guarantee that what the instruments that we've put together, right, is measuring the most important thing about reality. The fact that I have a thermometer to measure the temperature of the water over there, and can construct that thing that measures that quantity, that doesn't mean that the temperature of the water is something that is truly important for the dynamics of that water. Right?
Or even, correct me if I'm wrong, or even the fact that it's coming in as a tsunami, it's about to wash away the entire town.
Exactly. Right? There's no guarantee that that's the relevant thing to measure. So maybe what humans are stuck measuring so far just aren't good enough to pin down reality, but there is some underlying set of stuff that does determine crisply reality, restoring you from a probabilistic theory back to a deterministic one that says, okay, yes, if you had access to measuring, blue squiggly and red squiggly, then you would be able to tell from that exactly where this electron is at this moment and its position at that moment, and then from blue squiggly and red squiggly of this electron be able to say, oh yes, in 5 minutes it'll be over here with this momentum, deterministically exactly, right? And it could be as arbitrary as something that we call blue squiggly, red squiggly, not just like how humans name things, but something that is just so beyond our comprehension that maybe we'll just never be able to put together what that is in a fancy way. So he posited that there are these things called hidden variables that determine what is in what are the states perfectly, what is everything in a way that is deterministic. that nature isn't fuzzy, but it's sharp, and we just can't focus enough on reality to bring it into sharp relief. Einstein also, having done relativity, assumed that we didn't have things like superluminal speeds, and other such things. Now, there are actually a collection of these what are called hidden variable theories. Now, there are certain then assumptions you have to ask about what can these hidden variables do for you. One of the important ones that's very quickly given, that's complicated, so we won't go over too much of it, is this idea of a non-contextual theory. So measurements, it dips back into the philosophy of answering the question, if a tree falls in a forest and no one is around to hear it, did it make a sound? And a non-contextual theory will tell you yes, that there is a definitive value for a experiment you could make, regardless of whether anyone is making that measurement, right? So the answer is that a tree would make a sound, would give you a result for measuring the sound wave in the forest, even if no one was around to measure it. There's a couple of gentlemen, in fact, Bell. So along comes, right? So the hidden variable theories were an attempt to save some of these nice properties about reality that we liked. One of the other things.
So the crux of hidden variable is that, hey, it looks probabilistic, but that's only because you lack some critical piece of information that would have made it deterministic.
Yes, absolutely.
Okay.
And actually, before I move on, there's another thing that Einstein very much didn't like, something called entanglement. In particular, so what quantum mechanics tells us is that there's a way to kind of mix up two particles so that if one thing has one property, the other guy will have to have the opposite property. We'll go into defining that a little bit later, but when you go to measure quantum mechanically, if I find the particle, if particle one that came to me, let's say I have two entangled particles and I send them across the universe, one goes to you, one goes to me. If I measure my particle and I find that it's got one property, then when you measure your particle, will measure that it has the opposite effect, the opposite measurement, regardless of the fact whether you're sitting here across the table from me now or whether you're sitting over in the Andromeda galaxy. There's nothing in quantum mechanics that limits the distance that entanglement can happen, that entanglement can span. If two particles are entangled at one point, and then some amount of time later they're much farther apart, they're still entangled.
Okay, so correct my analogy. If I have two particles, let's say they have a color, and we separate them across the universe.
Mm-hmm.
I look at mine and it's black, therefore yours will definitely be white.
Yes.
Okay.
Yes. Yeah. Or you could look at yours and it would be white, but then mine would definitely be black.
Right.
Right. And there's as far as the mathematics of quantum mechanics gives, there's no reason why that correlation between measurement can't happen with this distance, or like I said, across intergalactic distances, which Einstein looked at, and having made special relativity and talked about, hey, with special relativity, stuff like simultaneity, things, the laws of cause and effect in special relativity are actually bound by a certain amount, right? In particular, I have to make sure that if I want to talk about event A being able to be the cause of some event B in the time distance space time, right? That B is within a cone followed by traveling out from A at a certain speed,
mm-hmm.
right? And in particular, if you can reach B by moving at a speed, basically an angle, that is less, right? This angle, right? That is less than the angle that you would get if you were traveling at the speed of light, then it's possible that A caused B. But if I have to move at a slope faster, let's say event C out here, A and C are what are called space-like separated. You would have to move faster than the speed of light in order to go from event A to get to event C. So if I throw a ball here and then across in 10 seconds in China, a young boy catches a baseball, those two, well, actually, let's make it real small. In a nanosecond.
Okay.
All right. In a nanosecond, just for the sake of reasonable times here. In a nanosecond.
Pretty impossible, but
yeah. If I throw a ball here and then a few nanoseconds later in China, a kid catches it, right? There's no way that those two events can be attached. There's no way that me throwing the ball can be the cause of the boy catching the ball.
Right.
Because they are space-like separated. That you would have to travel faster than the speed of light to go from one event to the next.
Which, to be clear, is a no-no as far as we're concerned.
Absolutely. Remember Einstein's, I guess we didn't actually go into that, did we? Yeah. Einstein's theories on relativity say, hey, nothing can actually move faster than the speed of light, and at best, massless things can move at the speed of light in a vacuum, right? Which also means that information can't travel that fast. So it doesn't matter, like, I cannot throw the ball physically fast enough for that ball to then land in the hands of that kid, right? That's basically what relativity tells us. So Einstein, having created that theory that says, hey, you can't have these faster than light event, like causations, right? I want to preserve some amount of locality, that events can only be caused by things that are within their local light cone, right? So that was what his...
Just for reference, that's a light cone you drew on the...
Yeah. So don't do this to me, right? This would be what the light cone would in the future. What we would be kind of talking about would be in the past, would be the opposite direction. So events that are going to be causally related have to be within each other's light cones, right? One is in the future of the other, one is in the past of the other, right?
Mm-hmm.
And if they're outside that, they're space-like separated. One can't cause the other. And those were the two things that Einstein really wanted to be able to answer with hidden variable theory. Some other people put on that bit of non-contextuality.
Which two things? I caught the locality part.
Locality and fuzziness.
Right.
Hidden variables in general get rid of fuzziness. Einstein really wanted to take care of locality, and some other theorists wanted to say, hey, maybe we can get rid of non-contextuality as well. Or maybe we can keep non-contextuality, right? Can we answer the question of if a tree falls in the forest, does it make a noise? The math on that one is a little bit messier. So we're going to go through not that, because there's a theorem that proves that you can't do non-contextual theories. But if you do allow yourself, well, maybe it's contextual. Maybe
that's a doozy.
Oh yeah. So there's a similar theorem. So Bell comes in and actually basically comes in and says, hey, quantum mechanics says you can't have all these things. I'm sorry, you're being too greedy. You had to pick two, and you tried to pick all three. So no, please get rid of one of these assumptions. Which is fun. Yeah. So I actually kind of like want to show you what Bell told about locally determined theories, and how quantum mechanics has No, you can't have those. Or rather, if you have a theory that has all of...
Oop.
That spiked. If you have a theory that has all of the nice properties that you want, that it can't reproduce quantum mechanics. So, one of the straightforward ways. So real quick, right? Let's go ahead. The way that you're going to probe quantum mechanics, is this basic picture. You're going to have a source of particles here, and it's emitting them along a line. Now,
Billy, cut my headphone volume just a little bit.
What you can end up with is, what we'll talk about here, fermions and bosons.
Too much.
And effectively the way that you will make measurements is, on an abstract level, the same thing. You'll send them through some sort of...
No, you just used a word there, fermion.
Yeah, we'll get there.
Okay. We're still talking about particles.
Yes. I send particles through a machine, and through the mechanisms of the machine, what will happen is this single beam, based on the quantum properties, will either deflect up and land on a detector up here, or deflect down and hit a detector down there, right? So if I send, each particle will have only one value for this. It's something called spin. It adds like how angular momentum adds, but it doesn't actually mean the particles are spinning. It's just the math matches, which is one of the fun things about physics. Oftentimes we're just trying to take math that like, maybe this doesn't work.
Spin has nothing to do with spin?
Yeah, spin has nothing to do with spin.
All right.
Physical spinning that I would think about spinning a ball on my finger doesn't necessarily have anything to do with what an electron is actually doing, but I know that it behaves in a similar way. If I try to add the spin of two particles together, it adds like how I would add angular momentum in like orbital mechanics or a basketball on my finger. For particles that are like electrons, what you'll use is something called the Stern-Gerlach machine, and basically it's a big magnet that makes sure. Why am I drawing the same thing? That makes sure that there's a magnetic field oriented in one direction, right? For a photon, another thing often common is you'll have a polarizer that will, based on whether it's whether the photon is spin up or spin down, or rather, excuse me, with photons, right? I guess we didn't get into what an actual photon is. So jumping back to the E&M equation, turns out light is its own medium for propagating through. If you remember that? I never actually did that, right? Yeah. We had clearly what we see as a wave, and we don't and we were left with there's no ether, so what the heck is happening? Well, it turns out that a photon is basically an electromagnetic field moving like this. Gosh, my drawing sucks. Then there is a magnetic field perpendicular to that.
Whew.
Oh, that's such a bad drawing. Well, unfortunately.
Maybe draw the line and then.
Yeah. Right, so if a photon is moving in this direction, right, there's an electric field here. And from this electric field in the direction of propagation, you actually know that the magnetic field is in the direction, is wobbling back and forth, kind of like this picture. But
can't see what you're doing, Billy.
Perpendicular to both of these directions. Perpendicular to this direction here and perpendicular to the up and down direction, which, on the iPad would be in and out of the iPad, but given that it's, a flat surface, that's kind of hard to draw.
Right.
Right. But you have these oscillating back and forth fields of E and B. And because of how it works, right, the math tells me that if I know two of these directions, I know the third. So if I know a photon is coming at me, then I only have to characterize either the E field or the B field, and then I know the other one.
Understood.
Right? Because of how the math works, it's easier to measure the electric field. So we characterize how a photon is called polarized based on how that tip is moving through space, whether it's moving along a line up and down, whether it's basically an arrow of constant length that's just rotating through space, or a side-to-side moment. What you can do is you can prepare photons so that they are polarized either up and down, horizontally, or vertically, or left-right, horizontally. And then you can have a device that sends the photon in two different directions based on whether it's polarized that way, right? If it's horizontal, it'll go in this direction, and then you have a detector, and if it's vertical, it'll go down and hit that detector. So, in a sense, these two...
It's basically the same premise.
Right. It's the same way of distinguishing the directionality, right? Whether the spin of an electron in a direction is up or down, versus whether the polarization with respect to a particular coordinate is along that coordinate or perpendicular to that coordinate. Now, an interesting and important bit of quantum mechanics is that let's say I measure an electron, and I measure it so it's so the Stern Gerlach is oriented so it's up down, so it'll send it either up, or it'll either send the electron up to my head or down to my feet. What the result of that experiment, right? I send a single electron through. Probability tells me the way that this will work out is the probability is that it's a half and half chance. Mm-hmm. And let's say it goes to my head. Okay, now I have information on how its spin was oriented in the vertical direction. But what that measurement doesn't tell me is the value of its spin, how it's oriented horizontally, left or right, or even along the direction that I'm sending that, whether it's, front or back, right? Now, in theory, I could measure those values. What I would do is I would take my Stern Gerlach and I would rotate, right? And then I could have it go to my left arm or my right arm. But the moment I make that measurement, I lose my ability to tell you anything about the up-down.
Why not both?
Because they erase each other. It's great. So think about experimentally how I would try and measure both. Well, okay, the way that I measured up-down was I put a Stern Gerlach like this. The way that I measured left-right was I put a Stern Gerlach like this. Well, if I put one here and one here together, what's going to happen? The superposition effect will tell me it'll pick a line, and it'll split up either this way on the line or that way on the line. So I have two different results. I can have two different results, the spin up or the spin down along that line, but it doesn't give me the additional information of how it splits up down versus left right, right? No matter how I try to take the measurement, I can't take a measurement of two quantities that are in the math of quantum mechanics we're going to call non-commutable.
Ooh.
Oh yeah. So the math of quantum mechanics is linear algebra, and so you use these things called matrices, and it turns out that if I have the operation of, say, matrix A, matrix B in one thing, and then I do matrix B and matrix A, I'm not necessarily guaranteed to get the same result from one ordering to the other.
So 2 times 3 is not the same as 3 times 2.
Yes, exactly that. In quantum mechanics, the orientation of your operations matter. The orientation of those numbers matter, right? It's very different from our normal happy intuitions about math and things like multiplication or whatever. But it's more akin to exponentiation, right? 2 to the 3 is different than 3 to the 2, right? Even though I've just swapped the order.
Or even like an airline pilot, right? If they rotate the plane and then they pull on the yoke, right? It's no longer doing the same thing.
Exactly. Rotations are another space where there's non-commutability in like the different operations you can do. It's important, the ordering. So that kind of ties back into that one measurement at a time, right? Basically, it's you can take a picture, right? But you can only measure along one axis at a time, basically. Yeah, it's great. But you can do the same thing whether it's an electron, whether it's a photon. It's fine. But yeah, so Bell comes across and says, "Okay, let us talk about the assumptions that we're going to talk about. We want our theory to have. What are the large scale things that we really want?" Right? Einstein said hidden variables should preserve these things that I like about my theory of special relativity. So one of the big ones, the big one, is something called local causality. Right? So quoting from an article from the Stanford Encyclopedia of Philosophy, Bell makes a particular thing in his, I believe, 1966 paper. And he introduces the principle of local causality, that the direct causes and effects of events are nearby, and even the indirect causes and effects are no further away than permitted by the velocity of light. Right? That idea that events A and B have to be within each other's light cones. But
that's what you explained before.
Right. That was partially this guy over here, right?
Right.
The idea that if they're going to be in a causal relationship, they have to be inside light cones. Now, Bell says this is not sufficiently sharp for clean mathematics, so he comes in with another slightly tighter, but more philosophically sounding definition. He says, a theory will be said to be locally causal if the probabilities attached to values of local beables in a space-time region, in a particular space-time region, let's call it space-time region 1, are unaltered by specification of values of local beables in a space-like separated, so say something like over here, region 2, when what happened in the backward light cone of 1 is already sufficiently specified, for example, by a full specification of local beables in a space-time region 3.
And a beable.
So, by beable, what he's referring to is an element of a physical theory that can be taken to correspond to something physically real. So, a beable would be a measurement of the distance between you and I, right? That is something that is physically real that can be verified by measurement. A beable couldn't be something like what is at least our current theories wouldn't be something like what is the emotion that I'm feeling right now, right? That's an experiential thing that's not necessarily predictable by physical reality. That's a perception thing.
So it's just strictly
measure things that you can measure effectively, things that you can measure directly. And until we get neuroscience to the point where I can take a scan of your brain real quick and then say, this is what you're feeling.
Right.
We won't consider that a beable. And then a local beable is something that is pertaining to a space-like region. Are those contained within that region? Right. So basically, things. I can talk about everything within here as being local to beable 1, right? Local to the space-time region 1. These are all local beables for this this area in the space-time diagram, right? And so what he's effectively saying is that, right, if go over the so effectively, yeah, right, it's possible that you could, let's say we have the Galileo experiment, but now we scaled it up to a giant Galileo holding a bowling ball and a feather a light year apart on either side of a black hole, and then he lets go. And the experiment is, how long does it take until they both hit the black hole? The event of him letting go the bowling ball and the feather would kind of could correspond to events 1 and 2, where right, you can actually come in and say, wait, these things are correlated, right? These things are correlated in a particular way, in that space-time event 4 actually causes them. Right? This is something that a guy called Reinbach came on with common cause principle, that things could be correlated, but not in a cause and effect relation if they have a common cause in their light cone history.
So number 4 is Galileo.
So number 4 would be Galileo thinking I should let go on both of these now. Now, there is a time that it takes, obviously, for the neurological signal to travel across his galaxy-wide arms
Of course.
and reach his hands and let go. And this is where that space-time region 3 comes in. I don't need to know all the information about Galileo's head, about the neurons firing at his head, if I have fully specified that at some place in his arm, here's the electric signal that's traveling to his fingers to let go. That's what Bell is talking about, how you don't need to know everything in the past of light cone of event 1 if you already have everything specified in 3. Knowing everything in its light cone in a layer 3 is enough should be enough to specify the events in light cone in 1.
So if I've got a huge stack of dominoes, I don't need to know that all the other dominoes fell. I just need to know that the second to last one fell.
Right.
Okay.
Right. I can if I look at the second to last one and then I can predict, hey, look, the last domino's gonna fall. Actually, like if we do the stack of dominoes, what if I have a trail that falls off? Well, as long as I'm only looking at one end of the trail, I don't need to know anything about the other end, the other possible trail.
Oh, the fact that it could still be going.
Yeah.
Right.
Right. As long as I'm looking at just one end and say, okay, when does this last domino on this trail fall? I don't need to know everything as long as at some point earlier in its trail I have everything specified. And that earlier point can still be outside the light cone of all the other trails. And it's still enough for me to determine the one trail that I'm actually interested in. Right? So that's the formulation, at least in words, of what Bell is trying to address when he's talking about what is local causality. But when you're doing these kinds of things, you're going to need to dive into math, right? Because proofs are all about making nice mathy bits. So for this, we're going to have to jump and do a little bit of probability theory.
Okay.
So I'm going to show you what the notation of this looks like. If I give you, let's say I want to know a coin flip, right? I'm giving you the probability of getting heads or tails of a coin flip. We'll call that X, right? What's the likelihood of getting a heads? If I give you a coin, if I have a coin and I flip it and I say, well, it's in the air, what's the likelihood of getting a heads?
Approximately 1/2.
Right? Because the way that you would intuit that is that, well, I know that coin has a head face and it has a tails face, right? And I have two possibilities, and I've got one possibility that I actually am being asked about, right? So 1/2. Aha. Well, I'm going to tell you you're wrong. Or rather, you don't know that it's approximately 1/2. You're making an assumption.
Mm-hmm.
You're assuming that the coin I'm flipping is a fair coin. It's possible I have some sort of cheat. I could have a double-faced coin. I could have it so that both faces are tails, right? That's not hard at all to think about. Or I could even be sneakier and adjust the distribution of the weight in the coin itself so it preferences one side versus the other, right? So I could have different results from what you expect based on something that you would need to know before the flip was made. So the way that we would normally kind of think about this is like the way that you were describing, right? Coin flip. I either have 1 or 0 based on the result here, right? X could be 1 or 0. But what we're going to have to take into account...
He's a little cut off on the screen.
Is it?
Yeah, you see the red lines that are in? Those are actually...
I didn't see that.
Yeah.
I didn't see that it was that far down. Okay. So the way that we're going to account for this in our math is we're going to instead say, okay, there's a probability on the coin flip. So the measurement is I'm looking at the result of a coin flip. And the probability is there's some result given information that I know. So in this notation, right, P of this whole thing represents the probability. So for a regular coin flip, right, I have a probability that is up and then down over heads and then up and then down over tails, right? If I give you a coin flip that's double-headed, it'll be here, and it'll be twice as high over the heads, and it'll be 0 over tails, right? This is heads, and this is tails. This would be heads, this would be tails. So the thing that's going to tell us the difference is this. So what is the probability of getting heads or tails, this X here, given that I know the weighting on the coin itself, given that I know whether it's a fair coin, a weighted coin, or a double-headed coin. So given, and then the coin, right, that little bit under there, represents what I am actually looking for in this probability, right? So the coin is what I'm looking at, like coin flip. X is the result of the coin flip. Okay. And then lambda is the piece of information that I would need to know to make an accurate guess on what this probability distribution is.
Is lambda a hidden variable?
Yeah. So when we go to how this is going to work mechanically, first let's really quickly guess that the universe itself knows everything. There's some perspective out there that God can see both experiment that I should actually give a way that this is going to give up. Okay. So what to account for this? And actually, perhaps we should go over more on this spooky action at a distance. I want to leave the quantum mechanical bits for later. But no, that's fine. Okay, we do need to talk about big picture bits. Particularly, we need to talk about entanglement, right? We talked about how they could be... Well, they could be attached. No, we did talk about that, right? We talked about how they could be correlated, entangled, so that, one of them has to be one way and the other one has to be the other, right? And that there's no distance that it's forced to behave that under, right?
They can be outside each other's light cones.
Right. There's no none of the math in quantum mechanics makes any explicit mention of the light cone, and so you could have them as far apart, right, that you would take the measurements on those particles as possible. Yeah. Because one of the things, as I was talking about, right, there are some measurements that you can potentially do at the same time. That's an important thing. There are communicable experiments that you can do, and I guess I should actually go into that. Specifically, so you can't measure, right, for the Stern-Gerlach, right? You couldn't measure the spin in the X and the Y at the same time.
Right.
But what I could do is I could measure the spin in the X direction, right? Whether it's spin up or spin down. And I can also measure the position, or no, not the position. I can measure the momentum of that particle in that direction at the same time. Spin measurements and momentum measurements are communicable with each other. I can actually, also interestingly enough, I can measure the position of a particle, for example, in one direction, and then measure the position in a perpendicular direction at the same time. Those are allowed. Those are operators that are what are called commutable. Those, they give you the same value regardless of the order you take them in.
And just to clarify, when you use the word operator, you're talking about making an observation.
Yes, when you make those observations regardless of the order. Yeah, you're right. The language that is used in quantum mechanics, right? You talk about operators, those are represented by matrices, yada, blah, blah.
Special forces, you're just looking at something.
Yeah. Yes, very much so. Oh, man. Right, so the way that you're going to try and check whether this spooky action at a distance actually happens is that you're going to have a source, right? A source of entangled particles, right? Call that S. And I send that one direction, and I send the other particle over here. This is physically possible to set up. There's an experimenter who has a Stern-Gerlach right here. Call them Alice. And we have a Stern-Gerlach over here, B. Bob. Yeah, classic information theory, right? And so they're going to be able to make measurements that send their particles in either up or down, right?
Mm-hmm.
Okay. That's the physical setup that we're going to have. So if we take the God's eye view of this probability, what we're going to end up with is we allow, let's say that the orientations that Alice could put her Stern Gerlach in, whether it's, measuring the X spin or the Y spin, is going to be measured by some A or A prime, right? We'll leave it general just because that makes the math apply regardless of what orientation. You could have these be 2 different degrees. In theory, you could have a multitude of different A values.
It could be horizontal, vertical.
Right. But these are the orientations that of the Stern Gerlach that Alice will say, okay, I want to measure what the spin is horizontally now. Or I want to measure vertically, or I want to measure at a 30 or a 60 or whatever, right? Mm-hmm. And Bob has basically the same choices, but we'll denote those as B and B prime. Okay. Now, what we'll have is that the result, let me see, just make sure that I'm consistent on this. Yeah. The result of Alice's experiment we'll call S. So the spin can either be spin up, we'll call it +1, or -1, right? The fact that it's a spin 1/2 doesn't matter. You can take the absolute value of it out, and you'll still get the maximum value or the minimum value, right? Bob will characterize his results by T, right? And again, it's the same particle, so it'll have the same potential results. It can either be 1 or it can be -1. Okay? So the God's eye view of this, the way that we will describe this with probability, is that the probability of the result of an experiment for where Alice measures her particle in the orientation A, and Bob measures his particle in the orientation B. The result, the likelihood that it gives result S and T, right? That it gives one result for Alice and another and one result for Bob, given some set of hidden variables. This is what our probability function will look like if you could look at everything all at once. God's eye view of the universe.
Okay.
Right? Where the universe knows what this lambda is. Now, who knows? There's a whole, since it's a set of measurements, right? There's a whole range of what lambda could be. So we'll call the space that lambda could be capital lambda, right? Big lambda. The entire space that T can be, we'll go ahead and call big T B. And then the whole space that S can be, we'll call big S sub A.
Just remind me again, so you have the A and then the A prime. What was the difference between A and then A prime?
So the difference is whether Alice is measuring...
1 second. Did it stop recording again? Did you start it? Okay. Does it time in? Does it clock in when you restart it? I think logic is just hitting the limit.
Oof, that's frustrating.
That's all right. We're good.
So this would be like A and A prime we're using to denote 2 different orientations that Alice could be making. So she could be...
so A could be horizontal and A prime could be vertical.
Right. So if Alice measures the horizontal, she will still measure the particle will give a result of either its spin up or its spin down. If she then, a moment later turns her thing so it's vertical and then measures, she will still get the same results if it's either spin up or spin down. But the space that you're sampling from is fundamentally different than the horizontal space that you had just a moment ago. So it's important to distinguish those two. So the full space has that little sub A to denote that will let you, like, if I'm actually writing out the specifics, I'll have, the space of all possible things that I could measure in the X distance, or space of all things that I could measure when I'm measuring Y, or when I'm measuring Z, if we get crazy here.
Okay.
Right? And then each of those spaces with this particular experiment has the same range. It goes from 1 to -1. Bob in the same way, right? His full space is going to be 1, -1 because it's the same particle, but he has the choice over what orientation he has, and we'll denote that with B.
Particle.
It's the same type of particle. Indistinguishability is a fun thing, right? Because interestingly enough, yeah, we can go ahead and jump on that. Interestingly enough, the thing that causes entanglement to work and actually happen is that we're required in quantum mechanics to make the math allow for indistinguishability between the individual particles, right? If I, let's say I'm back in, if you remember back in high school chemistry, you always heard that, a particle is specified by its quantum numbers, right? If we had the little Bohr model, right? You could specify what shell it was in, what subshell it was in. It's big shell, subshell. It's
S and P shell.
Yeah, S and P, and then so that's a orbital magnetization, and then what's the last one? Because it can be either plus or minus. Orbital magnetization, and I think angular spin number. I think that's enough to specify. I don't remember the titles.
Spin.
There's 2 different spins, unfortunately. Because the orbital one is like P shell, D shell, S shell,
right?
And then you have in those. Oh, excuse me.
I used to know the answer to this, but it's been
you have the shells,
yeah.
And then if you go to P shell, right? There's 3 different branches that you can go in P shell,
right? And
then once you're in that shell, you then have spin up or spin down within there. But if I specify that, right, that specifies fully the electron. But if I have, let's say that I have 2 chlorine atoms, and I choose and I'm choosing one atom that has one electron from them that they both have we pick from basically the same quantum numbers. If I pick an electron and then look at it, there's no way that I can tell which chlorine atom it came from. The electrons are indistinguishable. The analogy that back in the day with Benjamin Schumacher's quantum course gave is it doesn't make sense to talk about which electron you have in the same way that it doesn't make sense to go to the bank and ask for your penny, right? You may have a penny that they can give you, but when I give a penny into the bank and then ask for it back, there's no sense in asking for having my specific penny that I just gave to you.
Unless it was a defect.
Well,
right, yeah.
But then that's a distinguishability, right? You can distinguish pennies because they are macroscopic objects. But like in that analogy, right, we'll leave it and say, no, you actually can't, right? Electrons and protons and any quantum mechanical object, you can't distinguish between the particles beyond the quantum numbers beyond quantum numbers.
So this electron has a certain spin, a certain amount of kinetic energy, quote unquote.
Yep.
Okay.
Yep. And then you can't specify where it came from. If it's 2 identical systems, then you can't pick which one it came from. Now, because of that, the math forces you that if you to swap those 2 particles, you either have to have the same setup or you have to have negative that same setup. And so this actually is the distinguishing factor between what we call a fermion and what we call a boson. If something is a boson, then when I swap them, I get exactly the same picture. And if I swap 2 fermions, I get the negative of the same picture. I would get the negative measurement or something else. So the way that we account for that in the math, right? Quantum mechanics, I specify these algebra things called Brock-Ket. But if I had, say, now we get into it. If I have 2 particles stuck together, and let's say the thing that I can distinguish them by is their spin up or spin down, the way that this will have to work is normalization constant, roughly relevant for our bits here, is that I have to consider the point where particle 1 is spin up and particle 2 is spin down, or particle 1 is spin down and particle 2 is spin up. Now, in order to make sure it's a negative,
that is meant to be a ket, right?
this is a ket here, right? I have to have these two subtract from each other, so that if I take the two particles, right, if I had a little 1 and 2 on these, and 1 and 2, if I then looked at 2, 1 ket minus, yeah, we're getting real into the visuals here.
So, Billy so politely wrote, what the hell is a ket? The notation amongst us three is understood, but briefly, what is a bra and what is a ket?
Briefly, it's the math with which you specify your quantum numbers, the things that you care about quantum mechanically. It's right, they represent vectors in a linear algebra sense, but it's the formalism that you have to go to if you want to have your operators act as matrices, and then if you like act on them, have something recognizable pop out of it.
So in order to perform an observation or describe an observation mathematically as a matrix, then you would need to use this notation.
That is correct. Yeah. You could use a more expanded version of this, but this is the most compact version of that.
And this is known as Dirac notation?
Yeah, that is correct. Thank you for asking these details and to fill in the picture. Good times. So yeah, you have to use these fancy angled scribbling hieroglyphics. So let's specify this. If I have this guy here, when I compare the two, right? Yeah.
You don't have to write quite that small if you don't want to.
I know, it's the natural way that I write. That's my problem, unfortunately. Understood. So if I compare, basically, visually you don't necessarily need to do this, but it's the if I could distinguish it.
Zoom it in just a little bit.
If I could.
There you go.
If I could. Oh yeah, because I got to make sure it shows up on camera. If I could pretend for a moment that I could distinguish between the two particles from the two chlorine atoms, right? The math tells me that in order to keep indistinguishability, even if I could pay attention, that when I swap the two, right, I need the negative to pop up here. So if I compare these, what I find is that, the second one that I wrote is the negative of the first one that I wrote.
So it's the negative of the top line.
Yeah. Yep. Concepts. Why do you fail me? Learning a new app on air is always fun.
Oh yeah.
Right. All right. So, this is what it looks like for fermions. Aside from,
I think it's fair to say that the second line here looks like a superposition of what it was meant to be.
Oh yeah, because I have drug this piece over here. Oh, kill me.
So close.
It's painful. Let's get rid of that.
That's why we do it live.
Yes.
You know it's real.
Yep. Well, I mean, this is how I did tutoring. Was just like, oh, I did a thing wrong. Let me show you how to fix it.
10 times better than canned.
I can't.
No worries.
I can't figure something out. Well, now you get to watch the process. Now you get to watch the thought process as we try to figure it out. It's good. If you had.
So it's a beable. Oh my gosh.
Hey, I'm not. It's not my fault that Bell decided to invent words on me. Right? If you had a photon. Right. Or actually, doesn't even need to be a photon. If I had a boson, it would behave a little bit differently. it would be, I would look at, let's give it a slightly different symbol. I would have, let's say we're looking at polarization now. So I would talk about if it's moving, if I know it's moving in the z direction.
So we're polarizing particles now.
Yeah.
All right.
Well,
so let's just throw them right in the deep end of the pool.
No. We talked about polarization. We talked about, we did talk. So this was how you distinguished or specified how a light wave was moving through space, right? It's coming at you, and then
a light wave,
a light particle, a photon, something. We know light is a wave.
I'm just ribbing you.
Also, quantum mechanics tells me waves and particles are the same thing, depending on how you measure them. I'm not going to justify that statement. I'm sorry, audience. Deal with it.
No problem.
Right. So if I have photon 1 oriented in the polarized in the x direction, and then particle 2 would have to be also polarized in the x direction. And if it were polarized in the y direction, particle 1, then it would have to be oriented in the... Why did I draw side?
Definitely zoom in on that puppy a little bit.
Oh, yeah. Once I finish writing like this.
Maybe not that much.
Maybe not that much. Actually finish what I was drawing. Right, this is what a boson would look like. And what you'll notice is that if I were to swap this guy in the same way, if I were to swap the identity of the particles in the same way that I swapped the identity of the particles for these fermions, then I would end up with exactly the same thing.
Okay.
Right? So bosons are invariant under the swapping of identity, whereas fermions would be negative under the swapping of the identity. If we pretend that we can identify the particles.
Right. Okay.
Right? So the fact that I have to, in order to preserve indistinguishability, use these combinations in the most simple quantum mechanical wave function that I can describe according to the mechanics of quantum mechanics. If I'm trying to describe two particles at once, what I've drawn up here, these are the simplest ways that I could describe the two different particles. These are what are called the singlet states for a fermion and a boson. So this is the most simple description, the most with the least terms. If I were to go up in energies or
so basically my quantum numbers.
Yeah, if this is the smallest numbers possible. Now, if I make bigger numbers and more complicated wave functions, I don't get rid of the entanglement bit, right? And the entanglement comes from the fact that whenever I'm working with these wave functions, I have to have both of them, right? I have to have both the one where the first particle is pointed up and the first particle is pointed down. I cannot isolate them if I'm going to have indistinguishability. The moment that I measure the orientation of one of them, I've collapsed the wave function, and then I have distinguished whether I've got the up one or the down one. I can't describe to you whether I got the first photon or the second photon, but I can tell you whether you got the up or the down. And that's important because the moment I select, right, because the way this works, if you look at these brackets, right, the orientation of one is correlated specifically to the orientation of the other particle, right? If I know it's up, then if I know one is up, then I know two is down. And if I know one is down, two is up, right?
And is there any probability to this, or is it definite?
Probability to...
I've measured one, and I've determined it's up. So therefore...
So there is a probability in... So here, there is a probability in which of those two orientations you'll find it in, whether it's up, down, or down, up.
But once you've looked at
one and you know what value you get from it, whether it is up or down, then the other one is explicitly determined.
So I've effectively measured both by measuring one.
That is correct. Same thing with our boson boys. Right? If I look at the polarization, then I've determined the other. Because bosons have to be similar, right? They have to be the same, and electrons have to be opposite. Okay. So Oof. Back to,
Look at all this science.
oh man, yeah, there's still so much more math to go. Whew. So, if I've described to us, if I had the God's eye view of the entire universe all at once, this is the way that it would work, right? I would have the probability of, given the orientation that Alice decides to measure in and Bob decides to measure in, the probability distribution of the results that Alice gets and Bob gets, given the value of the hidden variables that no one has measured.
Okay.
Okay. So,
can you pull the context a little bit into view? Or you?
Yeah, the experiment.
I'd be like, do you check the amount of runtime we have left on the B-roll?
So, now, obviously, if I'm looking at this, sometimes it's important to be able to look at just the probability that, say, Alice would see, or just what Bob would see, given this setup. So the way that we would do that is we would take this global probability function, right, P sub A st, and we would just sum over all the results that you could get for Alice's experiment if I wanted to see Bob's, or for Bob's experiment if I wanted to see Alice, right? The way mathematically that's going to work is I'm going to have a probability function, let's label it as 1 for note keeping, that given Alice and Bob decide to measure one way, what's the probability that Alice measures something given hidden variables? And that's just, if I can find this just by taking the sum of all possible t, right? I take into account all the possible results that that Bob could get for his experiment, and I just sum it away, right? The opposite would be true for if I wanted to understand what's Bob's probability function, given that Alice and Bob have chosen a particular orientation, particular measurement. This would be the probability of selecting a particular t, a particular result for Bob's experiment,
right,
given hidden variables. And I do that by taking God's eye view and summing out all of Alice's results on the God's eye view probability function or probability distribution. Right? So with those notions set up, what I can say is I can actually put into words the causality argument, the causality condition that we talked about ages ago, right? That Bell was formulating, that if I have two space-time separated events, I don't want to have, event. Actually, this is finicky. If I have space-time event 1 and 2, right?
Mm-hmm.
I don't want there to be correlations between the two that are outside their past light cones, right? If they are correlated in a way that's still not cause and effect, but are correlated, I expect it to be some common cause in the background.
Now, who's making that assumption? Is this Bell or Einstein?
So this is Bell capturing the thing that Einstein wants in his theory.
Okay.
All right. So the idea is that hidden variables inherently take care of the fuzziness of quantum mechanics. So if I have if I have a hidden variable theory, then the fuzziness that's described in quantum mechanics is already gone away with, and the fuzziness I see is just that we can't get to those hidden variables, hence the name hidden, right? And now Bell is trying to say, okay, well, Einstein, you also want locality. You want to have things that are space-time separated to not be able to enter into a causal relation with each other, right? So the way that he's going to, that you specify that in mathematics terms is basically to say, if I have is first a thing we'll call parameter independence. Actually, you know what? Let me make it its own thing. So parameter end, right? Which is that if I for I'm going to note this. This FA stands for all. For all parameter settings A prime, B prime. So for all the different orientations that Alice can put her experiment in, and all the different orientations that Bob can put his experiment in, for all the hidden variable values that I could have, and for all the results that I could get from Alice's set of spaces, and all of the results for Bob's experiments, right? Then the following must be true, that the partial, right, the marginal probability of Alice measuring a result, given some hidden variables, for a particular orientation that Bob picks, right, is the same regardless of the orientation that Bob picks, right? So basically, right, the probability that Alice selects a result, regardless of whether Bob picks orientation B or orientation B prime, right, some other orientation, that probability distribution is indistinguishable, right? The distribution for Alice's results is indistinguishable based on how Bob chooses to orient his experiment.
Okay, so
right?
Bob can go in there and zoom in. So Bob could go in there and kick his machine, and it's not going to affect at all what Alice is going to get.
Exactly.
Probability distribution.
Right. And exactly the vice versa is true for Bob's results.
Now, this is still Einstein's assumption that has been codified by Bell.
So yeah, part of locality, right?
We're not claiming this is actual truth. This is just what Einstein is saying.
Yes.
This is an assumption.
This is because basically, right, if Bob, because the setup that you would have is to make sure that Bob and Alice are measuring, and so the events of them measuring are space-like separated from each other. So if they are space-like separated from each other, and therefore they can't influence each other, it must be that whatever Alice measures doesn't depend on the parameters of Bob's experiment, and whatever Bob measures doesn't depend on the parameters of Alice's experiment. So that's one of the pieces of locality, right, of quantifying in probability terms, right, in probability theory language, the notion of locality, local causality.
Okay.
Right?
Yep.
One of Now this is a piece of it. The next thing, I used up a lot more space than I expected on this, so we'll go here. The next bit is what we'll call outcome independence. Right, which is the notion that for all pairs of A, for parameter settings A and B, and for all possible hidden variable values and experiment results for Bob and Alice. This is T, big TB, right? It must be that what have we done? Give me the pen. Yeah. It must be it must be that the global view, right, the God's eye view, the universe that can see both experiments and tell you both results.
You mean the absolute truth?
Yeah. Right. If you're looking at the probability of the results of the experiments of both at the same time, right? What's the result of Alice and what's the result of Bob? That the results of those experiments, since same time is just inherent in space-time because it's weird, must be equal to the factorization, right, of basically the multiplication of the two marginal probabilities. Right? So God's eye view is equal to, the God's eye view distribution is equal to the multiplication of Bob's eye view and Alice's eye view. Right? Now, if I smash these two conditions, parameter independence and outcome independence together, the ultimate thing that I get that will categorize when locality is truly applied is a condition called factorizability, right? When the event of space is factorizable, then I have a local theory, right? So let's see what that mathematically will look like. So if a theory is factorizable, then for all orientations of Bob and Alice's machine and all hidden variables, then there exists marginal probabilities that there exists some experiment thing that is for Alice, has no knowledge of Bob, but given hidden variables, and there is some probability distribution, Bob's experiments, that has no knowledge of Alice, that the God's eye view probability function that depends on both and tells you the likelihood of getting a particular value for S and T, given your hidden variables, is equal to the multiplication of Alice's probability distribution that doesn't care about Bob at all and has no knowledge of it, and Bob's distribution that has no notion of Alice's. Okay. So this is slightly different from outcome independence, because before outcome independence, you could still have each of the, Alice in outcome independence, Alice's probability distribution could still be affected by Bob's orientation of his measurement. And in the parameter independence, the result of, if you have parameter independence, you haven't necessarily said that you can break apart the probability of Alice's measurement and Bob's measurement into two distinct, divisible quantities. You couldn't do a separation of variables on S and T.
Okay, so break this down a little bit conceptually for me. So if we go back up to parameter independence,
Mm-hmm.
What are we saying here? Like, this is, parameter independence is a formalization of one of Einstein's assumptions.
So, parameter independence is the formalization of saying that the choices that Bob and Alice make for their orientations, the measurements that they're going to make, cannot have an effect on the outcomes that they see. Okay. But what that leaves you with is needing to jump down is that, well, okay, maybe what they choose to measure doesn't affect anything, but it could be that Bob's measurement, what he sees, either plus or minus for that orientation, could come over and tell Alice's measurement what to respond with, or vice versa.
Okay.
So that's why we need that second piece. Outcome independence tells us that that Bob's outcome doesn't affect Alice's outcome. Not the orientation that they choose to put their experiment out, but the actual barring of superluminal messaging, effectively.
Okay, so the bowling ball hit the ground first. Does not affect the fact that the feather hit the ground second.
Absolutely.
Okay.
Right. The bowling ball hitting the ground first can't tell the feather to then fall second.
Okay.
Right.
Whereas the first one was whether I observed the bowling ball by sticking my foot under where it was going to land or taking a picture with a camera is not going to affect what the feather was going to do.
Correct.
Okay.
Good. Yeah. That is exactly what it would map to in the Galileo experiment thing. And so when
how you measure versus what you measure.
Right.
Okay.
And the factorizable, right? The factorizability condition says, okay, locality is kind of locality requires both of those things, right? So as is important to indicate, like what Bell talked about, is that factorizability isn't necessarily locality put into the language of probability, but what it is the consequence of locality being in your theory. If a theory is local, then it must be factorizable.
Okay.
So then contrapositive works. So like if it's not factorizable, then it can't be local.
Okay. And what made it local was the prior to assumptions.
Right. Yes.
Okay.
Mixing those prior to assumptions gives you factorizability, and therefore
understood.
Yeah. Now, so that's locality, which is the main thing that that Bell is looking at. But there are a couple other assumptions that are assumed and brought into. Specifically, Bell assumes that there are unique experimental outcomes. Right? Quoting from that Stanford Encyclopedia article, though it might seem that this goes without saying, the entire analysis is predicated on the assumption that of the potential outcomes of a given experiment, one and only one occurs, and hence it makes sense of speaking of the outcome of the experiment. The reason that this assumption is worth mentioning is that there is a family of approaches to the interpretation of quantum mechanics, named many worlds approaches, and some variants of the relational approach that hold that all outcomes occur in what are effectively distinct worlds.
Okay, so break that down, because that was a bunch of word salad.
So this goes back to how we were talking about the Copenhagen way of interpreting how you interpret seeing a value, a result for your experiment, right? Because when we are dealing with quantum mechanics, right, I don't have a way of determining exactly what value I'll get. Instead, I will get one of a range of different possibilities and I'll get them according to a probability. I'll get I'll get the value 1/3 of the time, and I'll get value 2/3 of the time, or something, right? So one way of interpreting how that works in the math is to say, right, the wave function collapsed, and so you're stuck with that one result, and that's what reality just chooses to give you. Another interpretation, another thing to try and explain that is to say, hey, no, instead, each measurement you ever make spawns enough different worlds where each of those results pop up, right? And
you just happen to be in the one.
You happen to be in the one where the result of your measurement is the one that you see, right? But effectively, they are distinct worlds. They're two realities that have no way of interacting with each other, right? That is the many worlds interpretation, and it's messy, but it's potentially a way that you could get out of Bell's theorem and still keep locality. So we assume that there is a unique experimental outcome, that it makes sense to talk about the result of the experiment, not a result.
Okay.
Right? Now, the third assumption, and this is the fun one, is that the choice of experimental parameters, right, what Bob and Alice choose as A and A prime and B and B prime, and the times which they choose to go for A or A prime or B prime, that choice is a free parameter. right? It doesn't matter what the lambda, what the hidden variables of the universe. Basically, the universe can be fully specified and nice and sharply focused, deterministic, without relying on that determinism also determining what measurements Alice and Bob decide to make.
Okay.
Right? So the idea is that it's the wrong one. So many fingery bits. Is that because so if you look at like this light cone argument, right? Eventually, backwards light cones from two space-like separated events will cross over, and so there will be regions like 4 where they could be a common cause. But the assumption is that there's not always a common cause for two events that are space-like separated to be happening, to be correlated that way. Another, and perhaps the better way to call it, is the free will assumption or no conspiracies assumption. So the assumption that you and I have the free will to choose, or Alice and Bob, have the free will to choose how they want to measure their system, and the universe hasn't conspired to make sure that they measure exactly this way at exactly this time, given the hidden variables of the universe itself. Or also that there's no conspiracy between measurement manufacturers, right? Because that's the thing, right? Because you could think of the world where the person who's making the apparatus that makes your measurements says,
scale.
No. Okay, whenever you see this, give it here so that in correspondence with this other machine that I've made, it'll measure this, right? There's a conspiracy, right? That would be a past event determining a correlation between space-like separations. We can generally assume that level of coordination is a bit hard, so we can assume it doesn't happen. And we want to assume that there is a certain amount of freedom in how you choose to measure, right, your system. Granted, that could be, maybe that assumption is wrong, right? Based on these three assumptions, Bell is able to derive some conditions on certain functions that if these three assumptions are true, right, specifically factorizability, unique outcomes, and free will are all true, then a certain function can't have a higher value than something. And what we're going to show is that if you have quantum mechanics, right, if you have the results of quantum mechanics, they go above that value. And it breaks it. You ready?
Yeah.
All right. So we've got our probability functions. The first thing that we want to kind of note is we want to talk about expectation values. So the average result of Alice's measurement, given that her and Bob are measuring in a particular way, is going to be, right, I take the sum over all of Alice's possible measurements, all of Alice's thing, and then the differential bit, I'm going to go ahead and just label that as 1, just so I don't have to write as much. And then I can also talk about the average, given the specific hidden variables, right, of Bob's measurement. And then I'm going to define, right, in the same way, I'm going to just measure over all possible values, that value times the probability of getting that value for Bob's partial differential bit, right? And no, this is going to be, a sub b, right? These parameters would match with what the subscripts of these probabilities would be, but I'm just going to ignore them for the sake of effective writing. And next, what I'm going to talk about is we have the expected value of both of them together. Right, so that would be sum over all of the possible measurements of Bob and Alice, and just take those results, multiply them together, and multiply them by the God's eye view of the whole experiment, right? So if factorizability is true, right, factorizability, then what I can say is that my my together expectation values for a given orientation of Alice and Bob is going to factorize into an expectation value for Alice that only depends on Alice's chosen measurement times a measurement for Bob that only depends on Bob's measurement.
Okay.
Right? That handwriting looks so much worse on the big screen.
Okay, because it's slightly blurred. You can't see that it's aliased on the actual camera.
Yes. All right. So now we're going to consider two different quantities.
Okay.
Right? So here is where mathy gets fun, and you just go, hey, here's a function that I happen to notice makes things break. Let's just consider this function. How many times a math proof uses the word consider is a light correlation to how much you're going to be hating yourself trying to read through it. So let us consider a quantity we'll call S that depends on a specific set of hidden variables and depends on the different branches, right? The different measurements that the different orientations that Alice and Bob could make. And we will take the absolute value of E prime for AB plus E lambda, the combined expected if Alice chooses the same orientation, but now Bob flips his measurement, plus the absolute value of the joint expectation if Alice chooses the different orientation, and then subtract from that Bob choosing the opposite orientation with Alice maintaining her same different choice, right? So basically, we have gone through all possible combinations of A prime, and B prime being multiplied together, right? You have A and B prime, A prime B, and A prime B prime. And the orientation of whether they are added or subtracted or stuck into absolute values is just going to be a consequence of how we're going to prove the theorem. This is the function that works, right? What does this S represent physically? It's a thing you can measure. And so because of how this method is going to work, that thing you can measure gives you a limit on what value you can expect from it if your parameters hold, right? The second thing that we're going to consider is S rho. So S rho is going to be basically the same thing, but now instead of just the absolute value, right, of the base expectation, we're going to look at the absolute value of the average of E, B, the average of E lambda over a distribution of possible values for the hidden variable lambda. Right? So basically, the first function that I defined for you was what would happen if I knew specifically what the hidden variable was. And this one is, what if I know the likelihood of selecting a particular set of hidden variables? Just draw this properly, and then we'll do minus A prime B rho.
You see it?
This would actually be a plus, excuse me, and that should be a minus in here. Prime B prime rho. There. Right. So what you've noticed, what you should notice is that basically the only thing that distinguishes these two lines that I've just written, S delta and S rho, is that one includes an averaging of the other, right? One includes one is the same function, but I've replaced the expected value with the average expected value over a distribution.
And just to be clear, the vertical line is the absolute value, and then the brackets are the
are the average. Yeah, it is annoying that we use brackets for both averages and brackets, but. I mean, there's a reason for that, but So what we know is that the absolute value of an average cannot possibly be greater than the average of its absolute value.
Absolute value of an average cannot be greater than the absolute value of the average.
The absolute value of an average cannot be greater than the average of its absolute value. So let's say, right, I have a random variable and it can go between -1, -2, -3, right? Then the average of that would be, let's say it winds up so it's -2, right? Then the absolute value of that average would be +2, right? Now, if I take the absolute value of those values, right? So the absolute value of all the possibilities would give me 1, 2, 3. And if I take the average of that,
write that down.
Yeah. So if I have, right, my random variable x, right, it can select from -1, -2, -3, right? Then what I'll denote as average absolute value, let's say these are all weighted by a third, so it'll be the absolute value of -2, which will end up giving me 2, right? And then I could also look at the average of x, which will be 1, 2, 3. And if the weighting is the same, right, and I've just taken the absolute value, so the weighting will be the same, then the average of the absolute value, basically
put this guy in the middle.
The swapping, yeah, I should. It's a good call. Then the average of the absolute value is here equal to 2. And basically, I cannot come up with a random variable x.
Can you move the whole thing up to the middle for a second? Yeah.
So that everyone can see?
Sure.
Yeah. I can't come up with any random variable x and any distribution over that random variable that breaks that. Nope. Give me that. There we go. That breaks. Let me make sure I get this right. Yeah. It breaks this inequality.
Okay.
Right?
So you're saying that always holds true?
Yes.
Okay.
Right? No distribution you come up with can break that, which, I mean, basically, the only thing that I could do to try and mess that up would be to introduce minus signs in special places. But if I'm already taking the absolute value,
I guess move that guy up a little bit.
If I'm taking the absolute value and then averaging, then I'm making sure I have only positive values. What I could potentially, when I'm looking at the average, I could have a mix of negative and positive values, and so those would cancel out. Versus if I'm looking at the average of everything where it's all positive, that's definitely going to skew to be greater. Make sense? Let me draw a picture. Right? Let's say I could have basically expected variables that look like this. Well, then the average of this would be x equals 0, right? Roughly. And so then when I take the absolute value, that's 0. But if I take the absolute value first, right, then that's going to look like this. And then all of a sudden, my average is here, right?
Right.
Because all of the stuff that was subtracting from the average before is now contributing to the average as I move over to the absolute value space, right? And then this is, it's not average. 0, 0. Make sense?
So far.
Okay. So with that specified, I have the condition that I can make. Specifically, and we'll get to why we chose these particular
Really check run times.
Function. We have straightforwardly that, actually, I'm getting a bit thin on, or thick on what I'm writing, so let me.
You running out of ink?
Yeah, because the line length, the line thickness stays the same, or scales with how I'm scaling this thing. That's annoying, but also fair. So we have this. What?
Well, we still have 3.5 hours available for B-roll and about an hour on A-roll.
Yeah. Well, we'll see if we can get through this in an hour.
I sure hope we do.
Oh,
I
man.
gotta cook steak pretty soon, man.
I'm here to make sure that it goes on forever. So we have this condition pretty readily, right? That is basically what I wrote before. If I average S with the specific delta known over that distribution, lambda or rho, and it's the same rho as that other function I said with S sub rho, then this relation holds, right?
Okay.
Can't be any greater. Now, factorizability implies if factorizability is true, then we get to have this relation at no matter what distribution I have for my hidden variables, the value of this function specifically is less than or equal to 2. Okay. So this bound is due to Clauser, Horn, and Chimney and Holt in a 1969 paper. Basically, it's a here they were making sure that if you didn't have perfectly anti-correlated or correlated measurements of how Alice and Bob chose to make their measurements, or if the quantum mechanical entanglement didn't always take, they always made sure this is the lighter restriction that makes sure that if you get above this, things are broken. Right. So, if we...
So that's basically our epsilon.
Yeah. So, let's go to... So the part that is going to prove Bell's theorem, which is... I guess I haven't stated Bell's theorem at all. So, the thing that shows what Bell talks about, that is, if a system is factorizable, has all three of your things, is factorizable, is uniquely determined on the outcome, and has no superdeterminism, then it cannot reproduce quantum mechanical probability functions. It cannot produce the probabilities, the results that we measure from measuring quantum mechanical systems.
So it cannot agree with reality.
Yeah, it can't. Yeah, if when we measure and we see, oh wait, quantum mechanics correctly describes things, right? It predicts things. This a theory that is factorizable cannot match that.
Okay, so you're saying right now that the quantum mechanics we know is not factorizable.
Yeah.
Okay.
So that's the well, okay, no, I'm actually not saying that.
Okay.
I'm saying that that's the happiest thing, and there are arguments for losing factorizability out of the three assumptions we start with may be the only way to account for where it breaks, but that's up in the air still, right? That quantum mechanics is either not factorizable or not super deterministic or not having a unique outcome. One of those things must be broken.
Okay.
And the one that people are most willing to let go, well, not even that people are most willing to let go, the one that potentially is the only thing that solves the problem is to let go of factorizability, is to let go of locality. There are advanced arguments that I don't feel like going into about apparently how if you lose both of, and actually I guess I should say potentially any combination of the two, but if you get rid of both of having non-superdeterminism and unique outcomes, it still might not be enough to allow for a localizable theory, a factorizable theory to reproduce quantum mechanics.
So the strongest of the three
is factorizability.
Is factorizability.
Yep.
Okay.
So let's show how this goes. The way that we are going to get this bound of 2 is that we consider the lambda, the specific one. If here I'm going to drop my A, B, and C's because factorizability, right? Remember that means that E can be broken up into big A times big B, right? So what we'll have is that it'll be A lambda that depends on A times B that depends on B plus b lambda that depends on b prime, close absolute value, plus, spiked out there, plus Alice's result that depends on her orientation a prime, and then b lambda little b minus b prime. And yes, this is part of why you were right when you said that visuals are important for this thing.
There's no way to
do math visually.
One person in the world will be able to follow it if you just speak the whole thing.
So we take advantage of the fact that A takes values, can either be positive 1 or negative 1. And since we have absolute values and a constant that we can factor out effectively, or a factor that's either positive 1 or negative 1, then the absolute value says, those both map to the same thing. And since, unity times anything is just whatever that thing was, I can say, hey, this is just equal to b lambda b plus.
So when they wrote this, they didn't just think to simplify the notation a little bit further.
Well, this is truly as simplified as you can get, because you need to specify.
Well, I mean, just like coming up with like a master function that says b lambda b comma b prime.
Yeah, because you want to be able to distinguish that you're talking about the specific value for the hidden variables versus whether you're talking about over the distribution of the hidden variables, right? Because that's exactly what we were just talking about here in this line before. Here is this guy, right? You have the actual value and then over the distribution, or the function that's just caring about the distribution itself.
Okay.
Right. So unfortunately, for the logic and keeping track of it, for the bookkeeping, so that you can follow the money, if you will, you need this level of notation. It's cumbersome, but yeah.
Welcome to science.
Ain't that the truth? So,
saw 2 rolling of eyes.
One thing that we can show with, like, you can convince yourself pretty easily, is that this is equal to 2 times the maximum value of either the measurement Bob makes for one orientation or the other. Right? Yeah. Like that. Right?
Okay.
Because, right, think if
As reasons.
Yeah, I mean, if this guy is this value plus a little bit extra, you'll get twice this value plus a little bit extra, and then here you'll get just one time minus once the little bit extra. Yeah. Right? Yeah. Yeah. Right here would give you. Do I want to actually go into the math? No, I'll leave it in words. So it's twice the maximum value, and then since these are either 1 or negative 1, the maximum value of that is just going to be 1. So hey, look, it's 2. So since the value here, if I take the averaging of S2, of the maximum S2, right, then this is the average of 2, which is just 2. Right? So the maximum value that you could have for any distribution, right, is 2. Where did I put that? Oh, here it is. Yeah. That guy here. So the maximum value for this function S, whatever it represents, over any distribution of hidden variables that you want, for orienting, right, a measurement for orienting, for comparing the difference between Alice orienting her experiment in one direction and another specified direction, and Bob also measuring in one direction and a different specified direction, then that function, if it is a theory that is factorizable, must be less than 2. Right? Yeah. So Now we have to ask ourselves, can we break that? And the answer is yes. Quantum mechanically, I can break it. So, right, we remember that's all the way up there. All right. Now, just
An infinite whiteboard.
we'll just redraw it because why not? So remember, this experiment can be done for bosons and fermions. So we are pushing up on a long time here. We'll go ahead and just do the fermion case, right? The fermion for this is going to be
What's going on, Billy?
right like this. Then if I wanted to plug that wave function and measure this e, the multiplied expected value, right? And the way quantum mechanically that this would look like is this notation, which will conveniently ignore explaining so that I don't bore the people at home with actual mechanics, but just the argument. And basically this is going to end up giving you this value. It's going to be 2 times cosine the angle between the difference between B and A, or the orientation of A. That is ugly as sin. Let's get rid of it. Right. So this allows for there to be not a perfect correlation, right, between how Alice and Bob orient their thing, right? They could be perfectly aligned, or there could be some amount of disagreement between them, right? In fact, the maximum value is if I choose if I choose all their orientations so that they all lie in the same plane. Let's like this. So the maximum possible.
Bring that puppy to the center.
Yeah.
There you go.
Prime would be this. So that the two sets of measurements that Bob and Alice could make, let's see, B A and then B A prime, right, is oriented like this, right? So effectively, I can get all possible if I look coplanarly at all possible mixtures of the orientations of B with B prime, or A with B prime, or A prime with B, right? The combinations that Alice and Bob can make, right? Then my S function, which is the thing we're measuring for specified, will assume that wave function specifies those hidden values. If it depends on the S function will be equal to.
And just a refresher, the S function is?
The S function was the thing that we had that cap on, right? S with a specific hidden variable specified should be less than 2, less than or equal to 2. So here, quantum mechanics tells us that the wave function specifies everything possibly known about the system. So the hidden variable should be specified in the wave function somewhere. Hence, S sub, the wave function that I wrote. This function, given that we know that E ends up being equal to that, will be the cosine of the difference between the A and B orientations plus the cosine of the angle between the A and B prime orientations, absolute value, plus the cosine of the difference between A prime and B.
So we can already see how it's going to be greater than 2, or could be.
Cosine. What am I doing? Prime, B prime. Yeah, absolutely. So once I've chosen to set it up this way, what we'll find is that these values where there's different primes, right? There's a prime variable and a not prime variable, end up having a value of theta, or no, excuse me, not theta, phi. And this guy here is 3 phi. So I'll end up with S lambda, or not S lambda, S, the wave function that we specified, being equal to the absolute value of 2 cosine that phi plus cosine phi.
Let this be a lesson, kids. Study your trig identities.
Yeah, it's so good.
Or don't. Just write them down on a chart.
Right, and effectively, right, when I make sure, so I have to check and see when does this break. And it turns out if I plug in, and I won't.
What's the squiggly between the rightmost cosines?
This?
Yeah.
That should be a minus sign.
Okay.
My hand is just bad at drawing small straight lines.
Yeah, I'll definitely get you a bigger iPad next time.
Yeah, that'll be helpful. In particular, if I then say, look, which value are we interested in? Well, the maximum occurs at S lambda 4, where you have 2 square root 2.
Lambda pi.
Pi, excuse me.
Okay.
Yeah, not lambda. So if I plug in for this theta pi over 4, I get something that's bigger than 2 by a noticeable fraction.
Indeed.
Right? So from that, what we can say is, hey, if I get quantum mechanical results, which is what happens when I have this expectation value here, right? For the expected value of A times B. If I plug it into that fancy S function that Bell came up with, I get a value that's greater than 2. And Bell showed that any theory that is factorizable can't have a value greater than 2. So quantum mechanics, in order to reproduce this function, right, this probability of this expected value from your quantum mechanical system, quantum mechanics, I can't have a locally determined system. So the hidden variables for this theory can't be locally determined, right? So
So there's something else.
Right, because the idea, because
I can't unring that bell. Wow.
The idea that Einstein tried to make is saying that, if we go back to the original setup of the experiment, is that if I have entanglement and, Bob's stuff over here determines Alice's stuff over here real fast, well, that's spooky. But what if they're determined right at the source? When they are made to entangle,
right,
they're locally next to each other. So they could be affecting each other.
Right.
Right? So maybe those hidden variables have to be locally determined. And if they are, I've saved my special relativity theory. But it turns out you can't have that if you want to have quantum mechanical predictions. Now, there are a couple of potential loopholes when you're trying to do this. There's the communication loophole. It's possible that, maybe you do this experiment wrong and Bob and Alice are just across from a table. And so while, technically if they do it right at the right time, it's spatially separated, it's space-like separated, but maybe it's not. Maybe you keep messing up consistently enough that there's enough time to communicate from one detector to the other.
So you're calling it a communication error?
Yeah.
But it's basically just experimental.
A communication loophole, because
the
loophole is maybe there's a time for communication between the two experiments, right? The other one is that's pointed out prominently is a detection loophole, which is the fact that whenever you're doing this, you're trying to since you have a probability function, the only way that you can really build it up is you never actually get access to the probability function itself, right? Instead, what you do is experimentally, you look at the frequencies of events and you estimate the underlying probability distribution of the experiment.
So you just have an imperfect.
Right.
Okay.
And so when you're doing this, right, you're going to have to count the number of pair production events with a certain outcome to the number of pair production events total. But it's frequently possible with these detectors that some photons fail to enter your detector. And sometimes you even have detectors that give you counts even if no photon is detected, like a dark count. So there's potential loopholes. Maybe no matter what you set up, you can't get out of these things being able to save locality. But shocker, we actually did do these experiments that are proven to be.
Obviously, the first one's
loophole.
pretty easy to solve, but
you have to make sure that you can get your entanglement to be far enough away.
Right.
Yeah. So experimentally, it's a bit hard.
But we're talking Earth-Moon distances.
Yeah. Well,
not even that, really.
Not even that, like local orbit, which is kind of what's happened.
Now the second one, repeat that second one again for me.
Which one? Detection?
Yeah, elaborate on the detection.
So the worry is as you are trying to build up these empirical counts, you need to calculate the ratio between the events that have a particular outcome you're looking at and the total outcomes, or the total pair production events. And what could happen is that, well, maybe like, an unfair amount or an incorrect amount of ones that are oriented with the first particle up,
right,
you don't get detected.
But so you're talking about a nuance of a specific experiment that utilizes pair production.
Yes.
So we're out of the realm of this thing where you set up a situation where you created entangled particles. I mean, not necessarily, but you can create this experiment without using pair production. Like you can do something else. You can just entangle some particles and then send them off on their way.
Yeah, that's fair. Well, the detection loophole is still potentially a problem with any time you want to make entanglement, because you could have entangle events, but they aren't detected by whatever instrument you have. But yes, it is an experiment-specific problem.
Okay.
Same thing with the communication loophole. It's an experiment-specific problem.
Right.
And we finally actually managed to do it with 3 different papers. The ones that are most statistically significant coming from the same issue, actually, of Physical Review Letters in 2015. Gustina et al. And Shalm et al. Have both very good results. Quoting from the account of those results, again from the Stanford Encyclopedia of Philosophy. Both of these experiments are based on transmitting 2 polarization entangled photons to remote laboratories where they are measured with high detection efficiency. These experiments use states that are not maximally entangled but are optimized in accordance with some particular math, and a maximal violation of a slightly different inequality than what I showed, but it allows for the inefficiencies in the detection loophole. The math on that is annoying, so we won't worry about that. In both of the experiments, the violation of that inequality was obtained at a high degree of statistical significance. Shalm reported a p-value of 2 times 10 to the negative 7, whereas Gustina a p-value of 3.4 times 10 to the negative 13, corresponding to an 11
better than medicine.
corresponding to an 11.5 standard deviation effect. So basically, you would have to get the likelihood of this effect just happening randomly versus it happening because of the correlation is a distance of 15 standard deviations, which if you do bell curve, that's huge. The probability of that happening is tiny.
Right.
like, I don't know. Well, yeah, like, 10 to the negative 31.
It's not impossible.
But it's not impossible. But also, welcome to science.
Yeah.
Everything we do with science is always just a better best guess. It's a really good guess, but it's just a guess. A very, very good one. So a very careful analysis of data, including space-like separation of detection events of statistical significance and of all possible loopholes, leaves really no space for doubt about their conclusiveness. Besides the detection and communication loophole, these two experiments addressed also the following issues: the number of emitted particles being independent of measurement settings.
A bunch of experimental crap.
Right.
Right.
So, yeah, they did a lot of cool stuff.
Neutrinos are, in fact, not faster than light.
So we do, in fact, have experimental proof that Bell's inequality is violated by a quantum mechanical system, verifying Bell's theorem. That if you want quantum mechanical probabilities, then it's going to break locality.
Very nice. Ready to eat some steak?
Absolutely.
All right.
Now, I mean, so really quickly, like, this is very important because it has some pretty potentially interesting stuff for like quantum information theory, right? Because that means you can use it for cryptography. You are there's nothing, right? There's nothing you can do as someone trying to intercept a signal that can affect the state of the particle you're measuring without ruining the entanglement and making it very obvious that your data has been interfered.
Let me point out, though, what an effective denial of service that is. Because if all I have to do is measure your photons to ruin your communication.
So it doesn't ruin the communication, but it's got clear signals of, oh, they've been tampering with this thing, which is the more important thing.
Right.
Yeah. Now, so we've already had this theory kind of puts prominently locality and local causality on the chopping block for our fundamental understanding of reality, even though
small reality.
Right. Even though, we kind of like intuitively assume that's how it should be, and special relativity kind of tells us that locality should be a thing. This is another one of those instances of better science coming along and saying, oh, you thought that better approximation you had was good? No, let's fix it. But it turns out it's not going to be the only thing that's on the chopping block it's not the last assumption, the last vestige of comfort that we hold on to that's actually on the chopping block thanks to quantum mechanics. And so when I come by and talk to you next, we'll go into that paper that I was talking about that inspired me to look down this quantum theory cannot consistently describe the use of itself. It was published in 2018, and the thought experiment
consistently describe the use of myself. So.
and the thought experiment, specifically one called Wigner's friend, which we'll get into, that maybe puts into question the absoluteness of the observed measurements that we have.
So it puts a limitation on how far that rabbit hole can go.
Yeah, it's gonna be interesting.
All right, cool.
Yeah.
Nature gives nothing for free.
It's the worst.
All right, man. Did we do color check? We forgot to do that. So
we definitely did forget to do color check.
So we can do that right now.
Does it? Oh, it didn't matter whether we did it at the beginning or end?
No, because I'll color balance at the end, and then I might even leave this conversation in here so people can see some of the movie magic.
We can see the bloopers. I mean, I don't know. That talk is going to be ugly as sin already.
What talk?
This whole production.
Yeah.
Me fiddling with the iPad being like, I don't know how concepts works. Maybe I should have touched this for like 10 seconds beforehand.
Nope, that is the way it goes.
Ain't that the truth?
There we go. Nice. All right, peace out.
What a good time.